Welcome to Sleepy Science. Tonight we're going to talk about the most relaxing facts about the cosmos, the kind of facts that make your mind feel calm and quiet. Out there in space, everything moves slow. Light travels for billions of years. Stars grow one breath at a time, and the universe keeps drifting forward like it has all the time in the world. As you listen, your body will relax. Your thoughts will slow down, and the universe will feel close, soft, and peaceful. Stay with me and let these cosmic facts help you fall asleep. And before we start, make sure to hit subscribe so you never miss another night like this. Close your eyes and imagine a vast, endless space stretching out in every direction. Galaxies, stars, and clouds of gas floating silently. You're just a passenger, gliding along, with nothing to worry about. Take a deep breath and feel yourself sinking into the calm. As you drift, let the universe whisper its secrets. The first thing you notice is the sheer size of it all. Distances are mind-blowing. Even the nearest star beyond the sun is over 4 light-years away. Light travels at 86,000 miles per second, but it still takes years to reach us. That's a lot of space to cross, even for something as fast as light. And the farther you look, the more your mind stretches to understand it. Galaxies cluster into groups, and those groups make superclusters. They form a cosmic web, strands of matter stretching across millions of light years. You're floating through one strand tonight, just quietly observing. The universe itself is growing. Imagine the fabric of space stretching gently and constantly. This stretching is called cosmic expansion. It's subtle, but it shapes everything you see. The scale factor is the tool scientists use to measure this growth. When the scale factor doubles, galaxies drift farther apart. Picture two dots on a balloon. As the balloon inflates, the dots move away from each other. That's how our universe expands. No one galaxy moves through space. Space itself stretches, carrying them along. It's slow on human timescales, but over billions of years, it's massive. This expansion isn't random. It's part of the universe's history, its story from the Big Bang to today. Scientists measure changes in the scale factor to understand how fast the universe grew at different times. They've found that it's speeding up now. Dark energy pushes galaxies apart, overcoming gravity's pull. It's invisible, mysterious, but powerful. Imagine a silent hand stretching space, moving everything gently away from everything else. That hand has been at work for almost 14 billion years. Distance in the cosmos is tricky. Light years help, but the numbers are hard to picture. A single galaxy is made of billions of stars, each a sun in its own right. Some galaxies are huge, spanning hundreds of thousands of light years. Others are tiny, dwarf galaxies with just a few million stars. No matter the size, all galaxies are carried along by space's expansion. And as you drift through this scene, time stretches too. Looking at a distant galaxy is like peeking into the past. Its light began traveling before humans even existed. Even the emptiest spaces are part of this story. Between clusters of galaxies lie cosmic voids. These are vast regions almost completely empty, millions of light years across. Imagine floating through one. Silence fills it. Nothing moves except for the faint pull of gravity from distant clusters. These voids shape the way galaxies move, guiding them along invisible paths in the cosmic web, shaping them along invisible paths in the cosmic web. The emptiness is peaceful, a reminder of how calm the universe can feel. Stars are born and die in this cosmic landscape. In giant clouds of gas, gravity gathers dust and gas into dense clumps. They collapse, and nuclear fusion ignites. Stars shine, some small and quiet, some massive and explosive. Those massive ones live fast and die young, exploding as supernovae. Their death spreads heavy elements into space, seeding new stars, planets, and eventually life. Even as galaxies drift apart, this cycle continues quietly in the background. You're floating through billions of years of stellar history, just observing. Your mind might wander to how tiny we are. Earth is a speck in one galaxy, which is a speck in a cluster, which is a speck in a cluster, which is a speck in the cosmic web. And yet, you're connected. The atoms in your body were forged in stars long gone. That dust traveled across space and time, eventually forming planets and life. Right now, as you relax, you're part of this cosmic rhythm. Each breath, each heartbeat is synced with the slow, steady unfolding of the universe. Space isn't completely silent. There's cosmic background radiation, a faint glow left over from the Big Bang. It's everywhere, but so weak you can't feel it. This radiation is ancient light, stretched over billions of years as space expanded. Tiny ripples in this light-seeded galaxies and clusters. The universe has been quietly sculpting itself from the beginning, and you're floating through that story, part of the quiet unfolding. Even gravity has its role in this calm dance. It pulls galaxies into clusters, shapes the spiral arms of galaxies, and guides stars around galactic centers. But it works slowly, over eons. The tug of gravity is gentle in the grand scheme, letting you drift without rush, carrying you across the cosmos at your own pace. So as you float tonight, imagine yourself riding along the scale of the universe. Past galaxies and superclusters, across voids and filaments. Imagine the fabric of space itself stretching around you. Let your thoughts expand like the universe, slowly, gently, without hurry. You're a tiny observer in a vast, expanding cosmos, and for now, there's nothing else to do but drift and watch. This is the first step on your cosmic journey. The scale of the universe is hard to grasp, but relaxing into it is easy. No need to measure or calculate. Just let your mind follow the stretch of space, the slow drift of galaxies, and the quiet hum of ancient light. Let it sink into your consciousness, carrying you deeper into relaxation. The universe has a shape, but it's nothing like anything on Earth. Imagine floating in space with no up, no down, no walls, no floor. The universe can be flat, curved like a sphere, or saddle-shaped. It's all about geometry on the largest scales, something impossible to touch but easy to imagine. Flat means parallel lines stay parallel forever. A triangle's angles always add to 180 degrees. Simple, steady, calm. That's the kind of universe that feels balanced, like gravity and expansion are in harmony. If the universe is curved like a sphere, space bends back on itself. Imagine walking in a straight line and eventually returning to where you started. It's strange to think about, but gentle. This curvature would slow expansion and might eventually cause everything to pull back together, collapsing slowly, like a cosmic inhale. On the other hand, galaxies drift apart forever, carried along by the infinite geometry of space. Scientists measure this shape by looking at matter and energy. They check the universe's total density. Too much matter? Curved like a sphere. Too little? Saddle-shaped? Just right? Flat. Tiny fluctuations in that light reveal the curvature of space. Everything aligns in a subtle, precise way, like a cosmic blueprint. Even small curvature affects the way light travels. Imagine a beam moving across space. In a flat universe, it continues straight. In a curved one, it bends slightly, changing the path you see. Light from distant galaxies carries clues about the universe's shape. Every photon, traveling for billions of years, whispers hints about whether we're on a flat plane or rolling across a cosmic sphere. Despite all the complexity, matter on the largest scales is surprisingly even. Galaxies cluster here and there, but zoom out hundreds of millions of light years, and the universe smooths out. This homogeneity means no spot is vastly denser or emptier than another. It's like a cosmic quilt, stitched evenly over unimaginable distances. This symmetry simplifies models and lets scientists make sense of everything from galaxy formation to cosmic expansion. Isotropy adds another layer. The sky's temperature, the density of matter, the glow of ancient light, it's all consistent. Combine isotropy and homogeneity, and the universe feels predictable and calm. You're floating in a vast, ordered space, and it's hard not to feel a quiet sense of peace. Even though the universe seems uniform, tiny fluctuations exist. Just small nudges, variations in density across space. These small differences became the seeds for galaxies and clusters. Gravity took over, slowly amplifying these ripples over billions of years. The universe's large-scale structure, the cosmic web, emerged from tiny differences in an otherwise smooth field. It's like watching a gentle breeze ripple a calm lake. At first, nothing seems to move, but eventually, waves form. Cosmic curvature also influences destiny. Flat means the universe will expand forever, but slowly. Open means expansion accelerates endlessly. Closed could eventually collapse. Each shape carries a story. Each story moves galaxies along invisible paths. Imagine drifting in space and feeling this silent pull. You can't see it, but you know it's there. Gravity, dark energy, geometry, they all shape the journey. Light traveling across these shapes stretches and bends subtly. Gravitational lensing occurs when massive objects curve space. Light from galaxies behind them bends around the mass, creating arcs, rings, or duplicates. Look at that arc and think about the invisible shape it traces. You're seeing curvature, not just light. It's nature's quiet way of showing you the universe's hidden form. Even emptiness tells a story. Cosmic voids exist between galaxy filaments. They're huge, empty spaces where few stars exist. The lack of matter in these voids affects the paths of surrounding galaxies. Gravity from clusters around voids pushes and pulls, guiding galaxies along invisible streams. It's like a calm river flowing through space, invisible but shaping everything. Cosmic structures also obey statistical rules. Clusters, filaments, and voids follow patterns predicted by physics. Even though space seems random, there's a method behind the apparent chaos. Understanding curvature helps scientists trace this method. It connects the dots between where galaxies formed and where they drift now. Floating through the universe, you witness the silent order behind apparent randomness. Galaxies themselves adapt to this geometry. Spiral arms twist under gravitational forces, but they also respond to the overall curvature of space. Filaments guide clusters, and voids shape flows. Everything is interconnected, like strands in a cosmic spiderweb. Drift for a moment and picture yourself moving along these invisible threads. The universe isn't just large, it's delicately structured, with gentle forces guiding everything in quiet harmony. Even on smaller scales, curvature influences light from distant stars. Redshift, the stretching of light due to expansion, changes subtly based on geometry. The farther light travels, the more space it moves through, and the more it carries a record of the universe's shape. You're not just seeing a galaxy, you're seeing billions of years of cosmic geometry encoded in photons. Imagine for a moment that you could feel curvature. In a flat universe, space feels endless and uniform. In a curved universe, it might feel like floating on a huge balloon or an infinite saddle. Your mind can't touch it, but your imagination can drift through it. That's the magic of cosmic geometry. It's everywhere, shaping everything, but completely silent. Even time interacts with shape. In curved regions, time and space are intertwined differently. Gravity and energy warp space, time slowing or stretching moments slightly. Cosmic expansion, curvature, and gravity all work together, creating a gentle rhythm that carries galaxies, stars, and even your imagination along. Floating here, time feels calm and elastic, flowing without rush. Everything in the universe, from photons to massive galaxy clusters, obeys this hidden geometry. Your body, lying still, mirrors this quiet order. Breathing in sync with the universe's rhythm, you become part of the cosmic story. Curvature isn't threatening or chaotic. It's a gentle guide, shaping paths over billions of years, smoothing flows, and creating the patterns you see across the sky. As you drift tonight, let your thoughts expand across curved, flat, and saddle-shaped regions. Imagine galaxies following invisible currents, voids pushing them along, and filaments connecting them like a silent network. Let the stillness of space, its vast geometry, and its slow, careful growth carry you deeper into calm. You're part of it, floating through shapes you can't see but can sense. Even the tiniest quantum fluctuation has traveled through this geometry, eventually forming stars and galaxies. Curvature doesn't just shape space, it shapes the path of everything in it. And as you float with it, your mind expands. There's nothing to do but watch, breathe, and feel the universe stretch around you. By the end of this drift, curvature and geometry are no longer abstract. They are gentle companions, guiding light, matter, and your thoughts. You're riding along cosmic highways, flowing through gentle bends, across vast emptiness, and along luminous filaments. There's calm in the order, quiet in the structure, and peace in the way the universe silently shapes everything around you. The universe is huge, bigger than anything you can imagine. But here's the thing, it's surprisingly even. Matter spreads out in a quiet, gentle pattern on the largest scales. Zoom out far enough, hundreds of millions of light years, and it's smooth. Galaxies cluster here and there, stars and nebulae shine in some regions, but overall it balances. No spot is overwhelmingly dense or empty. It's a cosmic calm, like a sea with tiny ripples, stretching endlessly in every direction. This evenness is called homogeneity. It's a fancy word, but it's simple to picture. The universe, at its largest scales, looks the same everywhere. If you floated far, far away and turned to look around, you'd see the same grand pattern. It's not perfect, of course. Small fluctuations exist, but these are just tiny whispers in the vast cosmic hush. The smoothness makes modeling the universe easier. It's like a blank canvas with just enough texture to grow stars and galaxies, but still calm, still balanced. Alongside homogeneity is isotropy. That's a word for looking the same in every direction. Stand anywhere, spin in a circle, and the universe feels unchanged. Cosmic microwave background radiation, the faint echo from the Big Bang, shows this beautifully. Tiny variations exist, just a few millionths of a degree, but overall, the sky glows evenly. This glow is ancient light traveling across space for nearly 14 billion years. It's a soft, quiet reminder that the universe is orderly. Even chaos has a rhythm here. This symmetry, homogeneity paired with isotropy, forms the foundation for everything cosmologists do. They assume the universe follows these rules to understand expansion, galaxy formation, and cosmic history. It's a safe assumption, and so far, the universe has mostly confirmed it. Even when you look at the tangled filaments of the cosmic web, the voids between, and the clusters of galaxies, the big picture remains balanced. Despite all this, calm, small ripples are essential. Tiny differences in density, just a whisper compared to the vastness, eventually grew into the galaxies and clusters we see today. Gravity gently pulled matter into lumps and threads. It took billions of years, but the quiet seeds of the early universe blossomed into stars, spiral arms, and cosmic filaments. Without these subtle variations, the universe would be smooth and empty, a quiet, featureless expanse. These ripples, small as they are responsible for all the dazzling structures you see in the night sky. Even the voids, those enormous empty spaces, are part of the story. They are quiet, massive gaps stretching millions of light years. Few stars shine inside them, few galaxies drift through, yet they influence everything nearby. Gravity from these low-density zones pushes and tugs on surrounding matter. Galaxies drift along invisible currents shaped by the voids, slowly moving through the cosmic web. There's stillness in these empty regions, but it's a dynamic calm, shaping the universe over eons. Think about the galaxies themselves. They move along these cosmic highways, guided by matter's distribution. Spiral arms twist and shimmer, clusters drift, and the web of filaments stretches endlessly. Everything is connected, from the smallest star to the vast filaments, and you, imagining this, are part of the calm floating through the ordered chaos. There's no rush. The universe doesn't hurry. It takes billions of years to evolve, to shape, to grow. That's why watching it in your mind feels so relaxing. Light itself carries messages about this uniformity. Cosmic microwave background photons traveled nearly 14 billion years to reach us. They tell a story of smoothness, of isotropy. Tiny temperature variations hint at where galaxies will form, but overall, the glow is even. Imagine looking up and seeing that faint echo of the Big Bang, feeling the quiet calm of a universe in balance. Each photon is a whisper from long ago, reminding you that space is vast, still, and gentle. Even though the universe seems quiet, there's action everywhere. Stars ignite, galaxies merge, black holes spin and launch jets. Yet the overall pattern remains homogeneous. The chaos of local events doesn't disturb the calm on the largest scales. It's like ripples on a placid lake. Waves form, sparkle, fade, but the lake itself remains smooth. That balance is what makes floating in cosmic imagination so soothing. Dark matter, too, follows this quiet pattern. Invisible but powerful, it threads through the universe, shaping galaxies and filaments. It doesn't shine or make noise, but it exerts gravity, gently guiding stars and gas. Without it, galaxies might not hold together, filaments could collapse. Its presence ensures the structure of the universe remains stable over billions of years. The universe's evenness depends not just on what we can see, but also on what we can't. And then there's cosmic variance, a humbling thought. We can only observe one universe, no experiments, no multiple trials. All our knowledge comes from this single vantage point. Some patterns might be random, some signals of deeper truths. It's a quiet reminder that our view is limited, but it doesn't diminish the calm beauty we can perceive. It's like floating in a vast ocean, knowing you can only see a small portion, yet still feeling the endlessness all around. On smaller scales, stars and planets form, galaxies cluster, and black holes spin. Yet zoom out far enough, and the universe smooths itself out. That's the magic of homogeneity and isotropy. Local events are dramatic, chaotic, energetic, but the big picture remains calm, predictable, relaxing. It's a rhythm that repeats, a pattern stretching across billions of light years, patiently evolving. Even cosmic rays obey this balance. They travel across the universe, influenced by magnetic fields, yet their overall distribution aligns with the large-scale structure. They rain down on planets, touch atmospheres, whisper faintly in your mind. Everything, even these high-energy travelers, fits into the cosmic pattern. It's like a hidden music playing softly, shaping the universe's calm structure. Galaxies drift along gravitational currents shaped by this large-scale uniformity. Some move toward clusters, some away from voids. They follow invisible paths, sculpted by matter's even spread. Over billions of years, these motions build the cosmic web, a delicate lattice connecting clusters, filaments, and voids. Imagine riding along these currents, flowing gently, no rush, drifting with the quiet order of the universe. Ancient light, cosmic background radiation, neutrinos, voids, filaments, they all tell the same story. The universe is calm on the largest scales, even as stars flare, black holes roar, and galaxies collide. That calmness, that gentle structure, is what makes thinking about the cosmos relaxing. You're floating through a universe that's chaotic locally, but harmonious globally, moving in slow, predictable patterns. As your mind drifts, picture the universe expanding evenly, smooth and balanced. Each galaxy moves gently, each filament stretches silently, each void holds space like a soft exhale. Homogeneity and isotropy aren't just scientific words, they're a meditation on calmness, on order, on quiet beauty. Floating through this, you feel the vastness, the gentle flow of billions of years, the slow evolution of everything around you. Your thoughts move along cosmic filaments. Light travels from galaxy to galaxy. Neutrinos pass unseen. Magnetic fields stretch across spirals. And through it all, the universe remains balanced, smooth, and serene. This calm isn't empty. It's full of gentle motion, quiet structure, and patient evolution. Let yourself drift here. The universe's evenness carries you. It's soft, slow, infinite, and comforting. Everything, from the tiniest fluctuation to the largest cluster, fits into this cosmic balance. And as you float in imagination, you become part of it. Homogeneity and isotropy aren't just rules. They're the rhythm of space itself, guiding galaxies, light, and your thoughts in a quiet, endless dance. Nearly 14 billion years ago, the universe was young, hot, and dense. Light couldn't travel freely. Photons bounced around in a chaotic dance, trapped by charged particles. The universe was opaque, a glowing fog stretching endlessly. Then came a quiet transformation. About 380,000 years after the Big Bang, the cosmos cooled just enough. Electrons paired with protons, forming neutral atoms. Suddenly, light could move without constant interruptions. Photons escaped, drifting through space for billions of years. This light is the cosmic microwave background, the universe's oldest signal. Imagine that glow bathing the entire cosmos. It's faint now, just a few degrees above absolute zero. But it carries a story written across time. Tiny ripples in temperature mark where matter would clump, where galaxies and clusters would eventually form. Each variation is subtle, nearly invisible, yet they were the seeds of cosmic structure. The universe was smooth overall, yet these minute differences shaped everything we see. It's quiet magic, a soft blueprint hidden in faint microwaves. When Arno Penzias and Robert Wilson stumbled upon this faint hum in 1965, they didn't know they were holding a cosmic relic. Their antenna detected a uniform microwave glow, a whisper from the early universe. No stars, no galaxies, just photons floating through time. This discovery confirmed the Big Bang, turning theory into reality. The universe's beginning became something we could measure, something tangible. Suddenly, cosmology had a foundation, a calm signal across the chaotic sky. The cosmic microwave background isn't perfectly smooth. Tiny temperature variations, mere millionths of a degree, hint at density differences. Regions slightly denser than average would collapse under gravity. Regions slightly lighter would remain sparse. Over billions of years, these small differences grew into galaxies, clusters, and the vast filaments of the cosmic web. The CMB is like a time capsule, a gentle snapshot of the cosmos before complexity. Looking at it feels like peering into the quiet nursery of the universe. Advanced telescopes, satellites, and detectors now map this ancient light with incredible precision. Every tiny fluctuation tells a story. Scientists measure these ripples to understand the universe's composition, its rate of expansion, and the influence of dark matter and dark energy. The CMB is like a soft background music, playing a melody of information across time and space. Its patterns are subtle, relaxing, yet they reveal the grand design of everything around us. Photons from the Big Bang carry more than temperature. They carry polarization, a gentle twist in the orientation of their waves. This polarization holds clues about the earliest moments, even hints of cosmic inflation. Inflation is the theory that the universe expanded exponentially, stretching quantum fluctuations into macroscopic structures. The faint polarization in the CMB is the whisper of that inflationary moment, a soft signature from the universe's first heartbeat. Studying this light connects us directly to the beginning. It's humbling, even comforting. You realize that everything around you, the stars above, the planets below, the atoms in your body originated from this same ancient cosmos. The air you breathe, the warmth on your skin, even the quiet rhythm of your heartbeat, all share a lineage with the universe's first photons. It's a subtle, cosmic connection, gentle and reassuring. The CMB also reveals motion. Our galaxy isn't stationary, it drifts through space. This movement causes a slight dipole effect in the microwave background, a tiny asymmetry showing our velocity relative to the cosmic frame. Even this movement is measured in microdegrees, almost imperceptible, but it reminds us that the universe is alive with gentle motions. Everything floats in quiet streams drifting through the calm cosmic sea. Beyond the CMB, there are other relics of the early universe. Primordial neutrinos, almost massless and invisible, stream across space. They decoupled from matter in the first second of the universe. Though nearly impossible to detect, these particles carry secrets of conditions far beyond what we can recreate on Earth. They're whispers from the first moments, a cosmic memory traveling quietly through time. Observing the CMB and these relic particles is like listening to the universe breathing. Each measurement, each tiny fluctuation is a soft exhale from billions of years ago. This light traveled through expanding space, stretching wavelengths in a gentle process called redshift. Galaxies drifted, filaments formed, voids opened, yet the photons from the Big Bang kept traveling, unhurried, silent, enduring. The uniformity of the CMB also tells a story about cosmic balance. The universe's large-scale smoothness reflects homogeneity and isotropy. It reassures us that despite local chaos, exploding stars, colliding galaxies, spinning black holes, the cosmos maintains a calm pattern overall. The CMB is the ultimate evidence of that serene order, a soft hum underlying everything that moves and shines today. Even the tiny anomalies in the CMB are fascinating. Cold and hot spots reveal the seeds of clusters, the gentle gravity wells that would draw matter together. Observing them is like reading a cosmic nursery rhyme, soft and rhythmic, guiding galaxies and stars into formation. Over billions of years, this soft pattern turned into the dazzling structures we now see in telescopes, in photographs, in your imagination. The cosmic microwave background also bridges space and time. It reminds us that we are looking back nearly 14 billion years. Observing the sky is like traveling on a gentle, unhurried wave. Light from distant galaxies mixes with ancient photons, letting us peek at the universe's infancy. Every star, every spiral arm, every glowing nebula is part of this continuum, shaped by the early calm and the subtle ripples of the CMB. Even phenomena like the Sunyaev-Zeldovich effect, where CMB photons interact with hot gas in galaxy clusters, are gentle whispers of cosmic interaction. These subtle changes let astronomers map matter, both visible and dark, across the universe. Each interaction is soft, slow, measured, yet it reveals deep truths about the cosmos. Observing the universe this way is like floating through clouds of ancient light, peaceful, calm, expansive. In the grand scheme, the cosmic microwave background is more than light. It's a guide, a storyteller, a gentle reminder of origins. It whispers of expansion, of inflation, of primordial fluctuations, and of cosmic patience. The universe started chaotic, bright, dense, yet it left behind a calm trail. The CMB carries that calm across billions of years, reaching you now, quiet and persistent. And as you imagine this light, imagine drifting along with it, through galaxies forming, stars igniting, filaments stretching, through voids opening, black holes spinning, neutrinos whispering. The universe's first photons move endlessly, serene, unhurried, guiding the cosmic story. It's a calm, continuous flow, a soft backdrop to everything we see today, everything we are, everything we might imagine. The microwave background is proof that even in a universe of violent explosions and massive collisions, there is balance, order, and gentle consistency. It's a cosmic lullaby, billions of years in the making, softly telling the tale of creation. Let your mind float with it, drift along the currents of ancient light, and feel the quiet majesty of the universe. The universe's earliest evidence rests in this faint glow. Every measurement, every tiny fluctuation, every soft whisper tells you the cosmos began, it expanded, it cooled, and it left a trail of calm behind. That trail reaches you now. As you imagine it, let it carry you gently. The Big Bang wasn't just a beginning. It's a soft, persistent presence, a cosmic heartbeat, an infinite lullaby stretching across time and space. The universe's story begins in the tiniest fraction of a second, a period so brief that time itself feels meaningless. Scientists call it the Planck epoch. Everything was compressed, unimaginably dense, hotter than anything we can picture. The laws of physics as we know them break down. It's chaos, energy, and possibility all rolled into one. Then, in the blink of a cosmic eye, inflation happened. Space expanded faster than light. Tiny quantum fluctuations stretched to immense scales, planting the seeds for everything we see today. These ripples were delicate, but they would shape galaxies, clusters, and cosmic filaments billions of years later. As space ballooned, it cooled, becoming less hostile. Particles formed, quarks combined into protons and neutrons, electrons began their slow dance around nuclei. For the first few minutes, nucleosynthesis occurred. Hydrogen, helium, and tiny traces of lithium emerged. The universe was still hot, still glowing, but it had structure. This period was brief yet foundational. Every atom in your body, every star around you, every cloud of interstellar gas carries the fingerprints of these first moments. Time kept flowing, and the universe entered a quiet age. Radiation dominated, light bounced around, and matter had not yet formed large structures. This was the cosmic dark age, a long stretch of stillness. No stars shone, no galaxies twirled. The universe was transparent in some ways, but opaque in others. neutral, hydrogen-filled space, absorbing ultraviolet light, keeping everything in a hushed, shadowed silence. After hundreds of millions of years, the first stars ignited. This moment is called cosmic dawn. Small clouds of gas collapsed under gravity, forming the first nuclear furnaces. These stars were massive, short-lived, and brilliant. They flooded the cosmos with ultraviolet light, breaking the opaque fog and ionizing hydrogen. Reionization began. Tiny pockets of brightness appeared, then grew, spreading warmth and light across the darkness. Galaxies began to form from these early stars. Gravity pulled matter together into clumps. Some clouds spun, flattening into disks. Others merged with neighbors, forming larger structures. Star clusters glimmered like sparks in a vast, dark sea. The Milky Way's ancestors were among them, forming quietly, patiently, billions of years before we looked up and wondered about our place in the stars. Every galaxy, every spiral, every elliptical traced its ancestry back to these first luminous islands in the dark ocean of space. Over billions of years, cosmic structures grew. Galaxies merged slowly, each collision a ballet lasting millions of years. Stars were born, died, and scattered heavier elements into the interstellar medium. Supernova explosions seeded gas clouds with carbon, oxygen, iron building blocks for planets, life, and everything in between. Black holes formed in the centers of galaxies, quietly shaping their surroundings with gravity and jets of energetic particles. The cosmic web took shape, filaments stretching across millions of light-years, voids opening like silent valleys. The universe continued expanding, stretching space itself. Light traveling through space was redshifted, waves lengthening as distances grew. Observers in the far future would see galaxies receding, the cosmic background cooling, and the universe aging. Relic neutrinos, almost massless, drifted freely, untouched by matter, preserving secrets from the first seconds. Cosmic rays traveled through magnetic fields, whispering stories of supernovae and black hole jets. Everything moved, slowly, inevitably, like a tide flowing across unimaginable expanses. Stars evolved in cycles. Some ignited, burning steadily for billions of years. Others exploded violently, releasing energy that lit up distant galaxies. Planetary systems formed around stars, some rocky, some gaseous. Dust clouds collected into protoplanetary disks, spinning, clumping, growing. The building blocks of life spread across the galaxy. Over time, planets cooled, oceans formed, atmospheres developed. The timeline of the cosmos is also the timeline of possibilities, the slow unfolding of everything that could exist. During these epochs, light traveled vast distances, carrying information across space. Observers in the far future could look at distant galaxies and see them as they were billions of years ago. The cosmic light horizon grew, slowly expanding the observable universe. Even today, there are regions beyond our reach, forever hidden, untouched by our gaze. Yet the light we do see tells a detailed story. By analyzing starlight, spectral signatures, and redshifts, scientists can reconstruct the universe's past, layer by layer, epoch by epoch. Every moment in cosmic history is linked. Inflation set the stage, nucleosynthesis provided the ingredients. Dark ages offered quiet cosmic dawn, brought light, galaxies formed, stars evolved, and structures grew. It's a seamless story of transformation, a calm yet dramatic unfolding of events across billions of years. Each stage built upon the last, patiently, methodically, like a symphony stretching across the universe. The timeline also includes violent events. Black hole mergers sent ripples through space-time. Gamma-ray bursts flashed briefly, outshining entire galaxies. Supernovae detonated, scattering matter and shaping galactic evolution. Despite their intensity, these events are rare on cosmic scales. They add texture to the quiet backdrop of expansion, subtle punctuation in a gentle narrative of creation. Cosmic timelines also reveal the influence of dark energy. As the universe expanded, its growth accelerated. Galaxies drifted apart faster over time, stretching the cosmic web. The forces shaping the universe aren't always visible. Gravity, dark matter, and dark energy quietly guide the formation of clusters, filaments, and voids. These invisible actors have been at work since the earliest moments, orchestrating the slow, calm expansion that carries the cosmos into its future. We can trace the ages of galaxies to understand cosmic history. Spectral analysis reveals the life cycles of stars within them, the periods of intense formation, and the chemical enrichment over time. This cosmic archaeology pieces together when stars formed, how galaxies merged, and how matter evolved from a dense hot soup into a structured, luminous universe. Each galaxy is a chapter, each star a sentence, the cosmos itself a long, flowing story, gentle and vast. Even the tiniest fluctuations from the earliest epochs have consequences. Quantum ripples from inflation, magnified over cosmic distances, seeded all large-scale structures. Tiny temperature variations in the CMB, subtle density differences in hydrogen clouds, eventually determined where stars and galaxies would emerge. The universe's earliest whispers continue to echo in the patterns we see today. Time in the cosmos is measured differently. A billion years is just a heartbeat in the universe's life, yet it's enough to build galaxies, spin stars, and form planetary systems. Observing distant galaxies is looking back in time, watching the universe grow before our eyes. Each photon is a messenger from a past epoch, a gentle note in the ongoing melody of cosmic evolution. The cosmic timeline is a reminder of patience. From Planck epoch to inflation, from nucleosynthesis to cosmic dawn, from galaxy formation to today, the universe unfolds slowly, inevitably, beautifully. It is a continuous, gentle flow, neither rushed nor chaotic. The stars, galaxies, and structures are the punctuation marks of billions of years of calm growth. They are the visible signposts along the universe's serene path. They are the visible signposts along the universe's serene path. And as you imagine these epochs, you float along with them. You drift through the early darkness, witness the first stars flickering on, glide along forming galaxies, and feel the quiet expansion of space itself. The universe's timeline is a soft guide, showing the gradual emergence of complexity, the patient dance of matter and energy, and the gentle unfolding of cosmic history. Space is bigger than we can imagine, stretching in every direction with no obvious edge. The farther we look, the more the past unfolds before us. When we gaze at a distant star, we are not seeing it as it is now, but as it was when its light began its long journey. Light from the nearest stars takes years to reach us, while the glow of distant galaxies has traveled billions of years. This cosmic delay is a gentle reminder. Looking out is always looking back. Every glance into space is a peek into the universe's memory, a way to trace its story from the very beginning. The universe has a limit, a boundary of what we can observe called the cosmic horizon. It's not a wall or a fence. It's simply the farthest distance from which light has had time to reach us since the Big Bang. Beyond that, the universe may be vast, may be infinite, but it remains hidden. Some regions will forever be unreachable, receding faster than light because of cosmic expansion. The horizon defines the edge of our knowledge, not the edge of existence. It's like standing on a shore and watching the ocean stretch into fog. We see waves, but the full ocean goes on quietly, patiently, beyond our sight. As the universe expands, this observable horizon slowly grows. Galaxies, once hidden, appear on the cosmic stage, revealing distant corners we could not see before. But the expansion is tricky. Some galaxies move away so fast that their light may never reach us. They drift past our cosmic reach, like ships disappearing over a horizon, and we will never know their details. The universe teases us with glimpses, hinting at infinity but keeping some secrets tucked away. This balance of revealing and hiding is part of its quiet charm. Light itself carries the message of the cosmos. As it travels through expanding space, it stretches. This is called redshift. Waves that left galaxies billions of years ago now arrive longer, softer, and redder than when they began. This stretching is subtle, but it tells astronomers how fast galaxies are moving and how the universe grows. The farther the galaxy, the more its light is redshifted. In a way, every photon is a tiny time capsule, whispering about motion, distance, and cosmic history. Released about 380,000 years after the Big Bang, it's the oldest light we can observe. At that time, the universe cooled enough for photons to travel freely. Before that, light bounced endlessly in an opaque fog of charged particles. That ancient glow now blankets the sky, a faint hum of the universe's infancy. Tiny fluctuations in temperature and density in this light reveal where galaxies would eventually form. These patterns are the blueprint of the cosmic web, stretching across billions of light years. Observing the cosmic horizon is like reading a layered diary. Every region, every galaxy, tells us a story from a different epoch. Nearby stars show the present, distant galaxies reveal the past. By mapping light at various distances, scientists reconstruct the timeline of the universe. It's a delicate puzzle, putting together snapshots from different eras. Each piece brings the universe into sharper focus, showing how matter, energy, and time interact to shape the grand structure of everything we see. Even the invisible matters. Dark matter weaves through the cosmos, guiding galaxies along gravitational currents. Cosmic filaments stretch like threads connecting clusters, shaping the universe's skeleton. We cannot see dark matter directly, but we see its effects in the motions of galaxies, the bending of light, and the formation of large-scale structures. These hidden scaffolds guide the observable universe, ensuring that matter follows paths dictated by unseen forces. Cosmic rays are travelers that carry secrets across space. High-energy particles from supernovae, black holes, and distant galaxies reach Earth constantly. They create subtle showers in our atmosphere, influencing clouds, auroras, and even the chemistry of the upper sky. These cosmic visitors remind us that the universe is interactive. Events billions of light years away can touch us in ways we barely notice. Observing these particles is part of understanding what is within and beyond the cosmic horizon. Some objects may never be observable. Due to the universe's accelerating expansion, some galaxies are already beyond the point where their light will ever reach us. They exist in a limbo, part of the cosmos, but permanently invisible. It's humbling. It shows that our view is limited, and no matter how advanced we get, some mysteries may always remain. Yet within these limits, there is still infinite beauty to explore. Every observable galaxy, every star, every photon carries a story. Time, distance, and light intertwine in this gentle dance. Observability depends not just on where an object is, but when its light began traveling. Looking farther is looking deeper in time. Ancient galaxies appear smaller, fainter, but richer in historical clues. Their light tells us about early star formation, primordial chemical elements, and the first structures of the cosmos. We see the universe's childhood, adolescence, and youth, all through the light that reaches us across billions of years. The universe is also noisy, in its own subtle way. Background radiation, cosmic rays, and gravitational waves all carry information about the unobservable past. Detecting these faint signals requires patience, precision, and quiet. Instruments like space telescopes, radio arrays, and neutrino detectors act like cosmic ears, listening to the whispers of a universe we can never touch. Each signal we decode is a gentle step toward understanding a universe much bigger than our own experience. The cosmic horizon also affects how we measure distances. A light year is simple for nearby stars, but billions of light years require adjusting for expansion. Space itself stretches, so the distance light travels is different than the distance to the source. Cosmologists carefully calculate these effects to map the universe accurately. These measurements are more than numbers. They are ways of connecting with a vast cosmos, a way to place ourselves in a timeline that spans everything from the first second to today. Even empty regions are meaningful. Cosmic voids, vast expanses with few galaxies, stretch between filaments and clusters. These quiet spaces influence how matter moves, how galaxies evolve, and how light travels. Voids define the cosmic web, shaping gravitational currents and providing context for the observable structures. They are the universe's pauses, giving rhythm to the otherwise continuous flow of galaxies and stars. As the universe ages, our horizon expands slowly, revealing new structures and histories. Instruments improve, allowing glimpses deeper into space. Yet we remain bounded by the speed of light and the universe's age. This gentle limitation is part of the cosmic story. It reminds us that seeing is a privilege, and that the universe's full grandeur is always slightly out of reach, quietly inviting us to imagine, explore, and wonder. As you drift through these thoughts, imagine yourself floating at the edge of what can be seen. The cosmic horizon stretches endlessly, dotted with galaxies, filaments, and whispers of radiation. Beyond it, the universe continues, silent and unseen. The horizon is both limit and invitation, defining the boundaries of knowledge while promising mysteries beyond. Observing it is a meditation, a way to feel the universe's vastness and our place within it. Every photon, every ripple, every particle reaching us is a message. They carry the memory of billions of years of cosmic history. Each one traces a path from an era we can only imagine. The observable universe is a delicate map, a record of what has traveled through space and time to reach us. It is both the edge of knowledge and a window into the infinite, a quiet bridge between the known and the unknown. And so, the cosmic horizon teaches patience, humility, and awe. It reminds us that the universe is bigger than our eyes, longer than our lifetimes, and richer than any single observation can capture. The stars, galaxies, and cosmic structures we see are threads of a tapestry that extends far beyond, weaving the seen and unseen into one calm, majestic story of the cosmos. Sometimes it erupts with brilliance that outshines entire galaxies. Gamma-ray bursts are among the universe's most explosive events. They are sudden flashes of high-energy radiation, lasting from milliseconds to minutes. Some come from massive stars collapsing into black holes. Others arise when neutron stars crash together in violent collisions. For a brief moment, these bursts release more energy than the sun will in its entire life. Yet, they vanish almost as quickly as they appear, leaving behind faint echoes in space. Observing them is like catching lightning in a jar. You know it's there, it changes everything, but it's gone before you fully grasp it. When a massive star reaches the end of its life, it can explode in a brilliant flash, scattering its material across space. These explosions are so bright they can be seen across millions of light years. In their fiery wake, they leave neutron stars, black holes, and clouds of gas and dust that seed future stars and planets. The debris drifts slowly, cooling over millions of years, providing the raw materials for new cosmic creations. Supernovae are both an ending and a beginning, a reminder that death in space leads to life elsewhere. Even smaller stars can surprise. Novae occur when white dwarfs in binary systems suddenly ignite in a nuclear outburst. The flare isn't as dramatic as a supernova, but it still brightens a star for days or weeks, signaling that something extraordinary just happened. Each eruption is a story, a snapshot of energy being released after eons of quiet accumulation. Watching these events is like reading the universe's diary, one explosive page at a time. Black holes, though invisible, announce their presence with ferocity. When matter falls toward a supermassive black hole, it heats up and glows in X-rays, forming powerful jets. These jets can stretch for millions of light years, blasting charged particles across the cosmos. They sculpt the intergalactic medium, regulate star formation, and sometimes even trigger bursts of new stars. Black holes are silent predators, yet their effects ripple outward, shaping galaxies and leaving a visible mark on space itself. Cosmic explosions often leave behind remnants that glow for millennia. Nebulae like the Crab Nebula are the aftermath of supernovae, clouds of gas illuminated by charged particles and magnetic fields. These remnants are vast, colorful, and serene in a way that contrasts the violence that created them. They drift slowly, quietly enriching space with elements like carbon, oxygen, and iron materials, essential for life and planets. In these quiet colors and forms, we can see the beauty born from cosmic chaos. Some of the most extreme events happen when neutron stars collide. These mergers release gravitational waves, ripples in space-time that spread across the universe. They also create heavy elements like gold and platinum, forged in the heat of the collision. The energy released rivals the power of 1 million suns for a few seconds. But when we do, it's like listening to the heartbeat of the universe, faint but undeniable. Even exploding stars can influence planets across light years. Cosmic rays, energetic particles from these events, travel through space and reach other star systems. They can trigger reactions in interstellar gas or even affect cloud formation on distant planets. On Earth, cosmic rays influence auroras and occasionally cause minor changes in atmospheric chemistry. The universe's violent events are subtle, yet their effects ripple far and wide, connecting distant explosions to life on a tiny blue planet. Gamma-ray bursts act like cosmic lighthouses. Their intensity is extreme, but they also guide astronomers to rare corners of the universe. By tracking the afterglow of a burst, scientists locate the host galaxy, measure distances, and study the environments where massive stars die. Each burst is a cosmic breadcrumb, revealing stories from galaxies billions of light-years away. It's amazing to think that in a few seconds the universe can share secrets that took billions of years to form. Some explosions are hidden from view. When a star collapses quietly into a black hole without a bright flash, it's called a failed supernova. The star vanishes almost completely, leaving little trace. These silent endings remind us that not all cosmic events announce themselves. The universe holds many secrets, some bright and dazzling, others quiet and hidden, yet all contributing to the grand design. The rhythm of these events is slow on human timescales, but steady in cosmic terms. Stars explode, remnants drift, neutron stars merge, black holes roar. Each process unfolds over thousands, millions, or billions of years. yet we can witness their effects in a single night of stargazing or through the lens of telescopes peering deep into space. Time stretches differently for us and for the cosmos. What seems fleeting to the universe lasts longer than we can imagine, and what lasts eons often appears as a brief flash to us. Magnetic fields often play a quiet role in these explosions. Charged particles spiraling along magnetic lines emit radiation, illuminating jets and nebulae. These invisible forces guide the motion of matter and energy during cataclysmic events. They help shape the aftermath, forming intricate patterns and filaments that stretch for thousands of light years. Even in destruction, there is order. The universe sculpts beauty from chaos, teaching us that energy and matter obey hidden, elegant rules. Supernovae also seed life. The elements ejected in explosions eventually form planets, water, and organic molecules. The iron in your blood, the calcium in your bones, even the oxygen you breathe. It all came from ancient stars that went supernova billions of years ago. Every explosion echoes through time, connecting distant stellar deaths to life on Earth. It's humbling and comforting knowing that we are literally made of stardust. Shock waves from supernovae compress gas clouds, triggering new star formation. A violent end sparks countless beginnings. These chain reactions build galaxies, light up star clusters, and slowly weave the complex cosmic tapestry we see today. Jets traveling near light speed carry energy so intense that they can distort space-time and emit radiation across the spectrum. Observing these events challenges the limits of technology. X-rays, gamma rays, radio waves, they all arrive carrying different parts of the story. By piecing these signals together, astronomers reconstruct explosions in ways that feel almost like reading cosmic whispers. Even faint explosions matter. Less energetic outbursts, like coronal mass ejections from stars, shape the local environment. Stellar winds push gas and dust, sculpting nebulae and influencing nearby star formation. Over millions of years, these subtle effects accumulate, subtly rearranging the structure of galaxies. The universe operates on multiple scales at once, from violent bursts to quiet nudges, all dancing together in a slow, intricate rhythm. Explosive events also help us test physics. Conditions near black holes or during neutron star collisions can't be replicated on Earth. By observing the light, radiation, and particles from these events, scientists explore extreme physics, high-energy reactions, and matter under unimaginable pressure. Cosmic explosions are laboratories for the universe, offering insights far beyond what we could create in a lab. The explosions are bright and fleeting, but the surrounding space holds serenity. Galaxies drift, voids stretch, and photons travel quietly through the dark. Observing these events from afar is a meditative experience. We witness violence without danger, chaos without fear, and brilliance without overwhelming the senses. It's a reminder that the cosmos balances fury with peace, showing extremes without tipping into disorder. Finally, each explosion is a story written in light and matter. Some are long gone, their signals just now reaching us. Some are happening this instant, yet unreachable. By watching these bursts, we connect across time and space. We learn about beginnings, endings, and the cycles that bind stars, galaxies, and the universe itself. In every flash, every jet, every expanding cloud, the cosmos whispers its history, and we, quiet observers, listen in awe. As we drift through space, the light around us tells a story. Not just any story, but the story of the universe itself. Light from distant galaxies travels for billions of years to reach us, but it doesn't come to us unchanged. The universe stretches as it grows, and that stretching stretches the light too. Astronomers call this cosmic redshift. When light stretches, its wavelength grows longer, shifting toward the red end of the spectrum. It's a subtle thing, almost invisible to the eye, but it holds the secret of how space itself expands. Imagine a galaxy far away, a billion light-years distant. When it emitted its light, the universe was smaller. Over the eons, space expanded, and the light stretched along with it. By the time it arrives at our telescopes, its color is shifted. Blues turn to reds, greens to oranges, and distant stars seem softer, cooler, gentler than they once were. This is not just a trick of perception. It's the universe speaking, showing us its slow, majestic growth over billions of years. Redshift is like a cosmic clock. By measuring it, astronomers can tell how fast a galaxy is moving away. Every shift in color, every tiny change in wavelength, is a piece of evidence for the universe's expansion. The farther away a galaxy is, the faster it seems to recede. This relationship was first noticed nearly a century ago, revealing that space itself is stretching, not just objects moving within it. Every redshifted photon is a whisper from a distant past, letting us peer back into epochs long gone. It's easy to think of light as static, but in reality, it's constantly changing. As space stretches, the light waves elongate, losing energy, growing fainter, redder. This is why the oldest light from the cosmic microwave background glows only a few degrees above absolute zero. Every photon carries the memory of its origin, yet it arrives at our detectors transformed, soft and silent, like a letter arriving centuries after it was written. Redshift doesn't just apply to visible light. Radio waves, X-rays, gamma rays, they all stretch. The farther a source, the more extreme the shift. Astronomers can use this to map the universe in 3 dimensions, tracking where galaxies are, how fast they're moving, and how cosmic structures are growing. It's a gentle measurement, yet it reveals the grandest motions imaginable, spanning the width of the cosmos. The effect of stretching light also lets us look back in time. Light from a galaxy a billion light-years away shows us how it looked a billion years ago. That's mind-boggling if you stop to think about it. When we gaze at distant stars, we aren't seeing them as they are today. We are seeing history itself. Cosmic redshift is both a telescope and a time machine, a way to travel backward through eons without leaving our own backyard. Not all light stretches evenly. Local movements within galaxies, gravitational effects, and interactions with cosmic matter can tweak the signals. But the large-scale redshift caused by the universe's expansion dominates over these local variations. It's a background rhythm, a steady pulse showing that space itself has been growing since the Big Bang. Every measurement we take confirms that this rhythm has been ongoing for nearly 14 billion years. Light stretching also impacts how we measure distances. A galaxy that looks faint and red isn't just far away, it's been traveling across an expanding cosmos. Its light has been diluted, its energy spread thin by the expansion. Astronomers account for this when they estimate cosmic distances. Redshift is a gentle but insistent reminder that the universe is vast, dynamic, and constantly evolving. Even everyday photons in space are affected. The radiation from stars in our own galaxy stretches ever so slightly as the universe expands. It's a small effect nearby, but over billions of light-years it becomes dramatic. Light from the edge of the observable universe is now microwaves instead of visible light. The universe is effectively cooling its own messages, slowing them down, turning brilliance into whisper. This stretching isn't random. It carries a pattern, a story of how fast the universe expands at different times. By comparing redshifts across billions of galaxies, astronomers can reconstruct the history of cosmic growth. They can see epochs where expansion slowed due to gravity and periods where dark energy accelerated the stretching. The universe leaves a record in light itself, a natural ledger of its past. Redshift also tells us about motion within galaxies. Some stars move toward us, some away, creating subtle shifts called Doppler effects. But cosmic redshift, caused by space expanding, dominates when we look at enormous scales. It's a reminder that the universe is layered. Small movements occur within vast trends, and the light we see carries both stories at once. One of the most stunning things about redshift is its scale. Galaxies billions of light-years away can have light shifted so much that ultraviolet radiation now arrives as infrared. What was once invisible to the eye becomes detectable only with special instruments. It's humbling. The universe's growth has transformed light across unimaginable distances, stretching it to the edge of detectability. Even ancient stars within our own galaxy contribute to this cosmic symphony. Their light is less stretched, but combined with millions of other stars, it forms a background hum that fills space. The cosmos is alive with light, constantly moving, stretching, fading, and sometimes brightening in bursts. Light stretching also shapes how we interpret distant galaxies. A faint red blob in a telescope might be a galaxy forming stars slowly, or a bright, active galaxy whose light has been stretched to invisibility in the visible spectrum. Astronomers must piece together clues across the electromagnetic spectrum to understand these distant objects. Every redshifted photon is a puzzle piece, a clue from the universe's past. Redshift reminds us of our place in space. We are observers in a growing cosmos, surrounded by light that has traveled for billions of years. Each beam carries history, carrying the story of creation, of expansion, of galaxies forming and drifting apart. The night sky is not static. It's a theater of light, stretched and slowed, a gentle reminder that the universe is immense, old, and endlessly fascinating. Even as we rest under these stars, the photons continue their journey. The light from distant galaxies we see tonight left them long before Earth existed. It has traveled across space, stretched by the expansion of the universe, carrying the memory of events that unfolded when life didn't exist anywhere. Observing this light is like eavesdropping on the birth of time itself. Finally, cosmic redshift isn't just a tool for astronomers, it's a meditation, a way to connect with the universe's pace. The universe grows slowly, quietly, and relentlessly. Light stretches gently, reminding us that everything moves, evolves, and transforms. Watching distant galaxies fade into red reminds us that time, space, and energy are in constant dialogue, whispering the story of the cosmos in a language we can almost feel if we only pause and listen. Far beyond the glow of stars and the spinning of galaxies, the universe hides whispers from its earliest moments. Tiny particles, almost impossible to catch, had been drifting through space since time was barely a second old. These are relic neutrinos, ghostly messengers from the newborn cosmos. They are nearly massless, moving almost at the speed of light, slipping through planets, stars, and entire galaxies without a single collision. They are everywhere, passing through you right now. Silent travelers from the dawn of everything. Neutrinos are shy. They barely interact with matter, which is why they've traveled untouched for billions of years. Think of them like cosmic ghosts, weaving through reality without leaving a mark. But their story is enormous. They were born when the universe was an unimaginable fireball, only a fraction of a second after the Big Bang. Back then, everything was dense, hot, and chaotic, yet in the midst of that turmoil, neutrinos began their endless journey. Once the universe cooled just enough, they decoupled from the plasma and started streaming freely, almost entirely invisible to the matter around them. Because they interact so little, relic neutrinos are incredibly hard to detect. Physicists have been chasing them for decades, building sensitive detectors deep underground, shielding instruments from cosmic noise. Even then, glimpsing them is like trying to catch a single drop of water in the ocean while blindfolded, and yet, the mere fact that they exist gives us a key to unlock the universe's first moments, a glimpse into a time we could never see with light. They tell us how energy and matter behaved in the first seconds, how the fundamental particles were distributed, and how the cosmic web began to form. Unlike light, which can be absorbed, scattered, or stretched, neutrinos glide unhindered. They are cosmic time capsules, frozen in motion, a direct link to the Big Bang. Every neutrino passing through your body is a message from the earliest universe, a faint, silent echo of creation itself. And they are not alone. Relic particles of many kinds fill space, left over from the extreme conditions of the young cosmos. Photons, neutrinos, and possibly other exotic particles form a quiet background, invisible yet omnipresent. They carry information about temperature, density, and energy in the universe's first moments. When scientists measure them, they are reading a diary written in the language of fundamental physics, stretching back billions of years. Neutrinos also connect the micro and the macro. These tiny particles, almost without mass, influence the largest structures in the universe. Their presence affects the formation of galaxies and clusters, subtly guiding how matter clumps together. The universe's scaffolding, its vast cosmic web, didn't evolve in isolation. Every ghostly neutrino slipping through space played a role in shaping the structure of the cosmos, quietly nudging it toward the patterns we see today. There's something poetic about that. These near-invisible particles, born in a fiery, chaotic universe, now drift silently across the cosmos, touching everything yet remaining unseen. They are reminders that the universe is more than what we can see. Even in the vast emptiness between stars, the tiniest whispers carry cosmic truth. Every neutrino is a testament to how delicate and interconnected the universe is, from its smallest quantum scales to its largest galactic stretches. Some neutrinos have traveled farther than any photon could ever manage. Light from the edge of the observable universe has been stretched and delayed by cosmic expansion. They just keep moving, practically unbothered, letting us, in theory, probe regions of space and time unreachable by ordinary observation. Scientists dream of detecting them not just to understand the past, but to test the very laws of physics under extreme conditions, to see whether the universe follows the rules we think it does, or hides secrets we haven't imagined yet. Neutrinos are also messengers of ongoing events. When stars explode, when neutron stars collide, or when black holes feed, neutrinos shoot outward, arriving long before light ever escapes. They arrive first because they hardly notice the dense matter that would slow photons down. They give astronomers a head start, a quiet alert from cosmic events happening millions or billions of light years away. It's like having a cosmic front-row seat, a first whisper before the universe shows its fireworks. Even though we rarely notice them, neutrinos subtly shape the universe we live in. During the early epochs, when the universe was dense, they carried energy that affected expansion rates, influencing how matter settled. They left subtle fingerprints on the cosmic microwave background, patterns in light that scientists can measure today. By studying these tiny ripples, researchers can decode the conditions of the early cosmos, learning how the universe expanded, cooled, and evolved in the first seconds. Neutrinos also connect life on Earth to the cosmos. The particles streaming from the Sun and from distant supernovae interact occasionally with Earth's atmosphere and oceans. Though they rarely cause direct effects, over billions of years they have subtly influenced cosmic radiation levels and energy flows. They are threads weaving together the local and the cosmic, reminding us that we are not isolated. Our planet, our bodies, even our very existence is intertwined with these elusive travelers. These ghostly particles make the universe feel alive in quiet ways. They pass through planets, stars, and black holes, unaffected by gravity or matter, like silent witnesses to all cosmic events. They are nature's subtle narrators, telling the story of the cosmos without fanfare, without light or sound. And yet, in their faint, persistent way, they reveal more about the universe than any blazing star or roaring galaxy. The more we study neutrinos, the more we realize how much they can teach us. They challenge our instruments, our imagination, and our understanding of the physical laws. They are both simple and profound. Simple in that they interact so little, profound in that they connect everything, from the first second after the Big Bang to the formation of galaxies, stars, and planets, to the very atoms in your body. And as we imagine all these relic particles drifting silently through space, it's calming to think that the universe has been whispering its story for billions of years, long before we arrived. Every second, neutrinos glide past, unseen but never absent, quietly telling the tale of creation. They are the ultimate cosmic companions, reminding us that even in vast darkness, the universe is alive with movement, history, and memory. So as you lie back, letting your eyes close and your mind drift, imagine these ghostly neutrinos passing through you, passing through Earth, carrying messages from the universe's first heartbeat. They've been moving through time and space without stopping, and tonight, as you rest, they continue their journey. They are timeless, invisible, and utterly patient, a reflection of the cosmos itself. And in that quiet, almost imperceptible way, they connect us to the beginnings of everything, the spark that started it all, and the silent, ongoing story of the universe. Far out there, beyond the glittering stars and spinning galaxies, the universe stretches into regions that feel almost unreal. These are cosmic voids, enormous pockets of space that seem empty at first glance. They span millions of light years, so vast that if you tried to cross one at the speed of light, it would take millions of years. And yet, they aren't entirely empty. Sparse gas, a few wandering stars, and traces of dark matter drift quietly, barely noticeable. These voids give the universe a sense of scale that's almost impossible to imagine. Silent deserts between islands of cosmic activity. Cosmic voids play a hidden but crucial role in shaping the universe. The matter around them, the galaxies and clusters, don't just float randomly. Gravity from these nearly empty regions pushes and pulls on surrounding structures, guiding galaxies along invisible pathways. It's like water flowing around rocks in a stream. The voids define the boundaries of cosmic highways, channels where galaxies travel over billions of years. Without these empty spaces, the cosmic web wouldn't have the elegant filamentary structure we observe today. Speaking of filaments, these are the universe's connective tissue. While voids are the quiet spaces, filaments are the bustling thoroughfares. Galaxies cluster along them, moving along gravitational currents like cars on a highway. Dark matter forms the backbone of these filaments, unseen but shaping the flow of ordinary matter. Gas and dust thread along, feeding star formation in galaxies caught in these streams. The cosmic web is like a three-dimensional map of matter, with filaments linking clusters and voids providing the negative space that defines them. Imagine floating through space and seeing this vast network stretch endlessly. Some filaments span hundreds of millions of light-years, and galaxies move along them as if pulled by invisible hands. The motion isn't random, it's orchestrated by gravity and the initial ripples from the early universe. Over time, these streams channel galaxies toward clusters where matter accumulates and cosmic fireworks occur. These flows help explain why galaxies are distributed the way they are, why some regions are densely packed while others feel deserted. Voids aren't just empty gaps, they're active players in the universe's evolution. Their low-density environment allows galaxies at their edges to move faster and interact differently than those in crowded clusters. Stars might form slower or faster depending on their cosmic neighborhood. Galaxies on the outskirts of voids often have unique shapes, influenced by the quiet but persistent push of the emptiness surrounding them. And in some voids, tiny primordial galaxies survive, nearly untouched by mergers or collisions, frozen time capsules preserving the early universe's memory. Filaments, on the other hand, are energetic spaces. Gas flows along them into galaxies, feeding star formation, igniting new generations of suns, and growing supermassive black holes at their centers. These structures funnel matter in a way that balances the universe, keeping clusters growing while maintaining the vast emptiness of voids. It's a cosmic tug-of-war, invisible but profoundly shaping everything we see. Even the light traveling from distant galaxies often follows these filamentary paths, making the cosmic web a kind of scaffolding for both matter and light. The interplay between voids and filaments is mesmerizing. Voids push, filaments pull, and galaxies dance along these forces in a slow-motion choreography that lasts billions of years. It's a delicate balance. Remove the voids, and the filaments collapse, destroying the network. Alter the filaments, and voids would lose their defining edges. Together they create a universe that is neither completely chaotic nor static, but a dynamic, evolving structure that is beautiful in its simplicity and complexity at once. Cosmic filaments also contain most of the universe's ordinary matter, the gas, dust, and baryons that eventually form stars and planets. Observing this matter is tricky. It's hot, diffuse, and faint. But scientists have found ways to detect it through X-rays and subtle absorption lines in light from distant quasars. By mapping filaments, astronomers can trace how matter flows through space, see where galaxies grow, and understand how the cosmic web sustains itself. These structures aren't just passive highways, they are lifelines, channels where the raw material of stars and planets travels, shaping the cosmos quietly but persistently. Some filaments are so vast that if you could travel along one at the speed of light, it would take hundreds of millions of years to cross. And yet, in the middle of this immense structure, the galaxies are tiny specks, each containing billions of stars, swirling dust, and possibly planets like our own. The contrast between the vastness of the filament and the smallness of the galaxies inside it is humbling. It's a reminder of just how immense and intricate the universe is, and how the emptiness of voids makes these structures even more striking. Observing voids is like peering into a mirror of the early universe. Because these regions are less affected by interactions and mergers, they preserve conditions closer to those that existed billions of years ago. Studying the edges of voids and the galaxies within can teach us about the formation of cosmic structures, the role of dark energy in expansion, and the distribution of dark matter. Voids are silent archives, storing clues about the forces that shape the universe and the subtle nudges that guide galaxies along their paths. There's also a poetic rhythm to all of this. Filaments stretch like veins across the cosmic body, connecting clusters like hubs of life, while voids are the lungs, empty but essential, giving space for the universe to breathe. Galaxies flow along these filaments as if moving with purpose, pulled by gravity and the ghostly influence of dark matter. It's a rhythm that has persisted for billions of years and will continue long after individual stars die or even galaxies collide. The universe is a living network, moving, shifting, and evolving in ways both predictable and mysterious. The relationship between voids and filaments also affects light. As light travels through these structures, it experiences tiny gravitational tugs and stretches, slightly altering its path. This effect, called gravitational lensing, lets astronomers map dark matter and see the unseen structure of the universe. Even the emptiness of voids bends the story of light, shaping the images we capture from distant galaxies. In a way, voids and filaments don't just sculpt matter, they sculpt our perception of the cosmos itself. And if you let your mind drift here, you can imagine floating silently through a void, surrounded by nothing but faint, distant galaxies, with filaments stretching out like glowing threads in the darkness. You feel the scale of everything, the slow, majestic movement of matter along invisible currents, the quiet push of emptiness, and the gentle pull of unseen forces. It's calming, almost hypnotic, a reminder that even in the vast emptiness of space there's structure, rhythm, and purpose. So as you imagine drifting along these cosmic highways, remember that every galaxy, every cluster, every star is part of a network shaped by voids and filaments. The emptiness isn't empty, it's part of the story. The threads connecting galaxies carry energy, matter, and time itself, and the silent voids define the space for the universe to grow. Together, they make the cosmos a place of order and wonder, a quiet symphony that's been playing for billions of years and will continue long after we are gone. And tonight, as you settle in, let your mind float through these silent expanses. Imagine the emptiness, the threads of galaxies, the invisible forces guiding everything, and the slow, steady expansion that carries it all forward. The universe is alive with subtle motion, even in the quietest voids. The cosmic web, with its empty deserts and luminous highways, is a gentle, infinite story, and you are a part of it, a quiet witness to the calm, enduring rhythm of space. Each galaxy carries its own story-spinning stars, drifting clouds of gas, and dark matter halos that hold everything together. Over cosmic time, these galaxies don't stay isolated. Gravity pulls them toward each other, and sometimes they merge, creating entirely new structures. Picture two spiral galaxies slowly drifting closer, their edges tugging at each other, stars flaring as clouds of gas collide, black holes at the centers dancing around each other in a slow, invisible waltz. It's a dance so slow it defies human perception, but over millions of years it reshapes the cosmos. Even our own Milky Way is part of this cosmic choreography. It's on a collision course with the Andromeda Galaxy, and while it won't happen for another 4 billion years, the merger will be epic on a cosmic scale. Stars are so far apart that actual collisions are rare, but gas clouds will smash together, triggering bursts of star formation, lighting up the galaxies with new stellar nurseries. And deep at the center, supermassive black holes will orbit and eventually merge, releasing gravitational waves that ripple through space-time. Galactic mergers aren't violent in the way we might imagine. They're more like slow, intricate constructions, rearranging the cosmic furniture over unfathomable spans of time. Galaxies evolve even without collisions. Gas slowly falls in, cooling and forming new stars, while older stars age and die, enriching the galaxy with heavy elements. Spiral galaxies can develop bars, elliptical galaxies may grow by accreting smaller satellites, and irregular galaxies twist and stretch under gravitational tugs. Dark matter, invisible but everywhere, provides the scaffolding. It keeps galaxies from flying apart, shapes their rotation, and even guides how they merge. Watching this evolution is like watching a city slowly expand, neighborhoods forming and disappearing, while invisible highways direct the flow of matter. Mergers come in different flavors. Some are minor, with a small satellite galaxy being absorbed into a larger one. Others are major, two galaxies of similar size colliding and blending their stars, gas, and dust into a new system. The aftermath is spectacular. Star formation often ramps up, fueled by the compressed gas clouds, creating bright pockets of newborn stars that glow like cosmic fireworks. Over time, the galaxy settles, sometimes forming a more massive elliptical shape, smoother and less structured than the original spirals. These mergers are a central way the universe builds complexity, turning simple systems into rich, diverse galaxies full of stars, planets, and black holes. Even tiny galaxies play a role. Dwarf galaxies, which might be overlooked on their own, often orbit larger ones, slowly being stripped of stars and gas. This feeding process helps larger galaxies grow while providing clues about dark matter's distribution. The remnants of these dwarfs can form streams of stars, stretching across a galaxy like ribbons of light, evidence of past interactions. Looking at these streams in the night sky is like reading a cosmic diary, tracing the history of mergers that have shaped the galaxies we see today. Mergers also affect black holes. Supermassive black holes at the centers of galaxies are rarely solitary. When galaxies merge, their black holes meet, orbiting each other and eventually coalescing. This process can release enormous amounts of energy, sending jets of particles shooting into surrounding space, sometimes triggering star formation or heating gas to prevent new stars from forming. The interaction between merging galaxies and their black holes creates a feedback loop, sculpting both the stars and the interstellar medium, influencing how galaxies evolve long after the merger is over. Galactic evolution is messy but slow. Stars born in bursts may live billions of years, dying quietly or exploding as supernovae. Gas clouds swirl and collapse, forming new generations of stars. Dust drifts through interstellar space, helping create planets, moons, and the complex chemistry that could, eventually, lead to life. The gravitational dance between galaxies reshapes everything but takes so long that it feels frozen from a human perspective. It's a gentle, ongoing process, almost like watching glaciers move, immense, slow, and majestic. Some mergers are spectacular. When two spiral galaxies collide, their disks can warp, arms stretch, and tidal tails form long streams of stars thrown outward by gravitational forces. These features are like cosmic fingerprints, recording the encounter's dynamics. Observing them in distant galaxies lets astronomers reconstruct the sequence of events that led to their current shapes, giving insight into the universe's ongoing evolution. Even galaxies that look serene from a distance may have undergone dozens of mergers in their past, quietly transformed by these gravitational encounters. Gas plays a crucial role in all of this. Cold gas clouds are the raw material for new stars. When galaxies merge, these clouds collide, compress, and ignite star formation. Hot gas expelled by supernovae or black holes can slow down this process, creating a delicate balance. Over billions of years, these interactions dictate whether a galaxy becomes a bright, star-forming spiral or a calm, red elliptical. The universe uses these mergers to recycle matter, distributing gas, dust, and stars in new configurations, constantly renewing itself. Even the faintest galaxies contribute. Low-mass satellites and tidal debris add subtle complexity, enriching larger galaxies with stars, metals, and angular momentum. These interactions leave imprints detectable with modern telescopes, streams, ripples, and shells in galactic halos that whisper stories of ancient encounters. By studying them, scientists piece together billions of years of cosmic history, understanding not only how individual galaxies grow, but also how clusters and large-scale structures emerge. Mergers are not just about the galaxies themselves. They shape the environments around them, affecting the intergalactic medium, redistributing dark matter, and sometimes triggering shocks that heat gas across hundreds of thousands of light years. They're like cosmic landscaping projects, slowly reshaping neighborhoods on a scale that dwarfs anything on Earth. Every merger is a chapter in the universe's story, a quiet but profound event that builds complexity, triggers change, and leaves lasting marks visible across space and time. And while this all sounds incredibly vast and abstract, it's worth remembering that the atoms in your body may have been part of stars born in galaxies shaped by these mergers. Somewhere in the universe, stars that formed billions of years ago in galaxies colliding with others eventually exploded, scattering elements that would one day become planets and life. Galactic evolution isn't just distant spectacle. It's connected to everything around you, linking our existence to the slow, majestic flow of cosmic events. So as you drift through this mental journey, picture galaxies slowly drifting toward one another, twisting, stretching, and blending in a cosmic waltz. Stars form, black holes interact, gas flows, and dust drifts along, all guided by gravity and time. It's a universe in motion, but the motion is gentle, slow, and mesmerizing, perfect to let your mind relax. The evolution of galaxies shows us that even the largest, most powerful structures change gradually, like breathing, swelling, and reshaping over eons. And tonight, as you let your thoughts float among these massive star cities, remember that every galaxy has a story written in motion, light, and gravity. The mergers, growth, and transformations aren't chaotic. They're part of a larger rhythm that's been unfolding since the beginning of time. You are part of that rhythm too, a quiet observer drifting alongside ancient stars, connected to the slow, graceful dance of galaxies across the cosmos. Galaxies are more than stars and gas. They are threaded with invisible magnetic fields stretching across thousands of light years. These fields are gentle yet persistent, shaping how charged particles move, guiding the flow of gas, and influencing how stars are born. Imagine a spiral galaxy. The stars spin gracefully, clouds of gas drift in wide arcs, and all along, invisible lines of magnetic force twist and loop, subtly steering the cosmic currents. These fields are weak compared to what we feel on Earth, but on the scale of a galaxy, they're powerful enough to affect entire star-forming regions, shaping the structure and rhythm of the galaxy over millions of years. Magnetic fields interact with cosmic rays. These cosmic rays are born in supernovae, black hole jets, and other energetic events. They shoot across space, tiny bullets of energy, colliding with gas and dust, weaving through the magnetic highways of their galaxies. Their paths bend and curve along magnetic field lines, creating a dynamic, invisible dance across interstellar space. Without magnetic fields, cosmic rays would fly straight, missing much of the galaxy. But with them, they spiral, scattering energy and influencing how gas behaves, sometimes triggering star formation or heating the medium around them. Cosmic rays are everywhere, constantly bombarding planets, stars, and interstellar clouds. When they hit Earth's atmosphere, they produce showers of secondary particles, tiny sparks that cascade down through the sky. Some reach the surface, and though most are harmless, they occasionally interact with our DNA, nudging evolution over immense timescales. Cosmic rays are the universe's subtle fingerprints, tiny messengers from violent cosmic events, carrying energy and information across unimaginable distances. Every burst, every collision, every particle adds to the silent rhythm of the cosmos, shaping galaxies in ways we're only beginning to understand. In galaxies, magnetic fields and cosmic rays work together to sculpt star-forming regions. Gas clouds drifting through space collapse under gravity to form stars. But magnetic fields can slow this process, twisting the clouds, resisting collapse, and controlling how quickly stars ignite. Cosmic rays add energy to the clouds, sometimes helping them collapse by ionizing particles, sometimes keeping them warm, preventing immediate star formation. The balance between these forces is delicate. It's like a cosmic tug-of-war, slow and gentle, yet over millions of years, it decides where stars will appear, how galaxies evolve, and how energy flows through the interstellar medium. These magnetic threads extend beyond the galaxy itself. They reach into galactic halos, the spherical regions surrounding the main disk, and even into intergalactic space. Cosmic rays traveling along these fields can escape into the broader universe, carrying energy far from their birthplaces. The combined effect is a galaxy that breathes slowly, expanding and contracting, shaping its surroundings with every particle and every twist of the field lines. Even invisible, these forces leave traces we can detect: radio waves from electrons spiraling along magnetic fields, gamma rays from cosmic ray collisions, subtle effects on gas temperature and motion. Scientists read these signs like a cosmic code, revealing the hidden structure of the universe. Magnetic fields also influence black hole jets. When supermassive black holes at the center of galaxies launch jets of particles, these streams follow magnetic field lines, spiraling out into intergalactic space. The jets heat surrounding gas, regulate star formation, and sometimes trigger the collapse of clouds into new stars. Magnetic fields give direction and structure to this enormous energy, preventing it from dissipating randomly and allowing galaxies to evolve in a more ordered way. Without these invisible guides, the energy from black holes would scatter chaotically, disrupting galaxies instead of shaping them. On Earth, cosmic rays interact with our planet in fascinating ways. They help spark the northern and southern lights, colliding with atmospheric particles near the poles, energizing gases and causing glowing curtains of green, red, and purple light. Beyond beauty, they subtly influence our atmosphere and climate. Some studies suggest that cosmic rays contribute to cloud formation by ionizing particles that seed droplets, a delicate dance linking distant supernovae to weather on our planet. It's amazing to think that events billions of light years away might touch us in ways we barely notice, connecting life on Earth to the vast, energetic universe around us. Magnetic fields and cosmic rays also help galaxies maintain structure over billions of years. Spiral arms are held in shape partly by the interplay between gravity and magnetic forces. Cosmic rays moving along the arms add pressure that counteracts gravitational collapse in certain regions, smoothing the flow of gas and preventing runaway star formation. Magnetic tension stabilizes clouds, while cosmic ray energy regulates heating, creating a rhythm that lasts for eons. It's a slow, intricate system, invisible to the eye but essential to the life of a galaxy. Even in seemingly empty regions, these forces stretch far. Cosmic rays can travel thousands of light years from their sources, threading through magnetic fields that guide them, influencing distant star-forming regions. Magnetic fields don't stay static either. They twist, tangle, and reconnect, releasing bursts of energy that ripple across the galaxy. This ongoing motion keeps galaxies alive, active, and dynamic, even when stars are quietly spinning in the night. The galaxy isn't still. It hums, flows, and breathes, powered by invisible forces dancing across cosmic distances. Relics of cosmic rays and magnetic fields carry stories of the universe's past. By studying them, scientists uncover the history of supernovae, black hole activity, and galactic evolution. Patterns in cosmic rays tell us where stars exploded, how particles propagated, and how energy moved across space. Magnetic field structures reveal spiral arms, galactic halos, and interactions with neighboring galaxies. Every measurement, every subtle fluctuation is like reading a diary written in invisible ink, a record of cosmic events stretching back millions and billions of years. Magnetic fields even shape galaxy clusters, the largest gravitationally bound structures in the universe. Gas between galaxies, called the intra-cluster medium, is threaded with fields that guide particles, regulate temperature, and affect star formation indirectly. Cosmic rays traveling through clusters interact with these fields, creating shocks and heating gas over millions of light years. Clusters become living laboratories, where forces invisible to the eye orchestrate slow, magnificent changes over eons. As you imagine this, picture a galaxy as a vast, spinning disk, stars glimmering like distant lanterns, gas drifting in spirals, all while magnetic lines weave through the scene, invisible but real. Cosmic rays streak along these lines, tiny sparks racing at nearly light speed. Clouds collapse into stars here, explosions send energy there, and jets from black holes carve paths outward. Everything is connected: motion, energy, gravity, and magnetism, creating a subtle cosmic rhythm. It's slow, majestic, and quiet, perfect for letting your mind drift, settling you into the soft glow of the universe. Magnetic fields and cosmic rays remind us that the universe isn't just stars and planets. It's a living, breathing system with unseen forces guiding the flow. They shape galaxies, regulate star formation, connect events across light years, and even influence life on tiny blue planets like ours. Observing these forces lets scientists trace energy, motion, and history across time, understanding the cosmos in ways that go beyond what the eye can see. Even though they are invisible, they leave tangible fingerprints in light, gas, and particle motion, revealing the dynamic complexity of the universe. So tonight, as your thoughts drift among galaxies, imagine the invisible threads wrapping around stars, guiding energy, shaping cosmic cities, and the high-speed messengers racing along them. The universe hums with motion you can't see but can feel in imagination, a gentle, endless dance of magnetic fields and cosmic rays, breathing life into galaxies over billions of years, helping the cosmos stay alive, structured, and quietly magnificent. Supermassive black holes sit at the hearts of galaxies, silent and invisible, yet they wield an astonishing influence. They don't just sit there quietly sucking in matter. They can launch streams of charged particles into space at near-light speeds, forming jets that stretch across millions of light years. These jets act like cosmic sculptors, shaping their galaxies and the surrounding intergalactic space. Imagine a river of energy, narrow but unstoppable, carving paths through gas and dust, heating the medium, and influencing where stars can form. These jets are violent yet graceful, explosive yet rhythmic, and they unfold slowly enough that the galaxy feels their influence over millions of years. Black hole jets start when matter spirals into the black hole, forming a superheated disk of gas and dust. Magnetic fields twist around this spinning disk, funneling some material into narrow beams that shoot away from the poles. These beams carry tremendous energy, enough to affect star formation and redistribute gas across the galaxy. In a way, the black hole acts like a gardener, trimming some areas while allowing new growth in others. The jets can prevent runaway star formation, heating surrounding gas so it can't collapse too quickly. But they can also compress gas clouds, triggering bursts of new stars in just the right spots. They can extend far beyond the galaxy itself, reaching into intergalactic space. They're like invisible highways, connecting the center of a galaxy to the broader universe. Gas clouds drifting through space feel their presence, cosmic rays accelerate along their paths, and the overall structure of the galaxy subtly shifts over time. These jets are both destructive and creative. They carry energy away from the black hole, preventing the center from collapsing too quickly, while also redistributing matter, seeding new star formation, and sculpting the shape of the galaxy. Observing black hole jets is like watching a cosmic performance. Radio telescopes capture the spiraling paths of electrons moving along magnetic field lines. X-ray telescopes detect shock fronts where jets collide with gas, and gamma-ray observations reveal the highest energy emissions. Together, these signals tell a story of energy, motion, and transformation. Scientists can trace how jets shape star formation, influence galactic evolution, and even impact the growth of neighboring galaxies. These jets are more than violent bursts. They are the organizers of galactic neighborhoods, the invisible hands that shape cosmic architecture. Jets also interact with interstellar gas in dramatic ways. As the beam pushes through gas clouds, it compresses, heats, and sometimes blows material away. This interaction regulates the supply of gas available for forming stars. Too much energy and star formation is suppressed. Just enough, and it can trigger bursts of new stars. Over millions of years, these interactions carve cavities, create shock waves, and form elongated structures within galaxies. The galaxy becomes a living, breathing system, continuously shaped by invisible energy flows that ripple outward from its central black hole. In some cases, jets are responsible for colossal radio lobes, enormous clouds of energized plasma extending beyond the galaxy. They're silent, invisible to the naked eye, yet they contain enough energy to influence entire galaxy clusters. The presence of these lobes hints at the black hole's history, telling scientists about past bursts of activity and how energy has traveled across millions of light years. They are cosmic fingerprints, delicate but enduring, leaving a mark on the universe that lasts far longer than the stars themselves. The motion of jets is guided by magnetic fields, twisted like threads in a cosmic loom. These fields channel particles, keep the beam focused, and allow the energy to travel immense distances without dispersing. Without this invisible guidance, the jets would spread out, dissipating their energy before reaching far. With it, they remain narrow and directed like a laser across the cosmos, reaching beyond the galaxy to shape distant gas clouds. The combination of gravity, magnetism, and motion creates a slow, majestic dance, orchestrating the evolution of galaxies over millions of years. Jets can also impact galaxy clusters. The energy they deposit into the surrounding medium prevents gas from cooling too quickly, which slows the formation of new stars in certain regions. In some clusters, jets create bubbles in the hot intra-cluster gas, rising like invisible balloons and redistributing energy. This delicate feedback loop keeps galaxies and clusters in balance, preventing overgrowth while allowing new structures to emerge. It's a cosmic balance of creation and destruction, driven by forces invisible to our eyes but detectable through careful observation. Sometimes jets collide with neighboring galaxies, injecting energy into their gas and altering star formation. These interactions can trigger new waves of stars, reshape galactic structure, and even redistribute dark matter indirectly by influencing the motion of gas. The influence of a single black hole can ripple across millions of light years, subtly guiding the growth of the cosmic web. Jets are like the universe's sculptors, carving shapes on the grandest scales, working slowly but with precision, leaving fingerprints across billions of years. While they seem violent, jets are also rhythmic. They flicker, change direction slightly, or vary in intensity as the black hole consumes material unevenly. These variations echo across the galaxy, influencing how gas flows, where stars ignite, and how the interstellar medium evolves. The galaxy feels the heartbeat of its black hole, a slow, steady pulse that reminds us everything in the cosmos is connected, from the tiniest particles spiraling into the singularity to the farthest stars in the outer arms. Jets aren't just limited to visible galaxies. Their influence can extend into the vast emptiness of intergalactic space, shaping the distribution of gas between galaxies and altering the paths of cosmic rays. They contribute to the heating and motion of the diffuse plasma that threads the universe, subtly guiding structure formation on scales far beyond individual galaxies. Their impact is invisible but undeniable, like a quiet wind shaping the landscape over centuries. Observing jets gives us a glimpse into extreme physics. Inside these beams, particles reach energies far beyond what we can achieve on Earth. Magnetic reconnection, shock acceleration, and relativistic effects all play a role. Studying them helps scientists understand not only black holes but the fundamental laws of physics, linking the smallest particles to the largest structures. Each observation is a window into both cosmic history and fundamental science, showing how the universe operates at its most extreme. As you imagine these jets tonight, picture streams of energy shooting out from a dark heart, weaving through stars and gas, shaping galaxies over millions of years. They are violent yet gentle in effect, destructive yet creative, sculpting the universe in ways invisible but profound. Each galaxy, each star cluster, carries the signature of these cosmic sculptors, reminders that even the most distant and powerful forces are part of the delicate rhythm of the universe. Black hole jets remind us that the universe isn't static. It's alive with motion, energy, and subtle guidance, a complex interplay of forces that sculpt galaxies, regulate star formation, and influence cosmic evolution. They are part of the invisible machinery that keeps the universe balanced, dynamic, and quietly magnificent. The jets are the heartbeat of galaxies, sending ripples across space and time, shaping the cosmos slowly, elegantly, and forever. Long before our sun even flickered to life, the universe was in a quiet darkness, stretching and cooling after the Big Bang. For hundreds of millions of years, nothing glimmered. No stars, no galaxies, just a vast sea of hydrogen and helium drifting silently. This era is often called the cosmic dark ages, but it wasn't empty. It was full of potential. Tiny fluctuations in density, seeded during inflation, were slowly gathering mass, tugging on each other with gravity, laying the groundwork for the first luminous structures. Then, gradually, the first stars ignited, and with them the universe awoke. This period, known as cosmic dawn, marked the beginning of light in the cosmos. It was quiet at first, gentle bursts of ultraviolet radiation escaping from these earliest stars. They were small compared to some of the massive stars that would follow, but their impact was monumental. Each photon of light carved a path through the neutral hydrogen fog, slowly ionizing gas and creating bubbles of transparency. The universe was starting to illuminate itself, and the first galaxies were taking shape. These early galaxies were unlike the majestic spirals and ellipses we see today. They were small, clumpy collections of stars, messy and chaotic, like cosmic nurseries. Gravity pulled gas into dense knots, triggering star formation in short, intense bursts. Some of these stars were enormous, many times the mass of the sun, and they burned hot and fast. They lived brief, brilliant lives before exploding as supernovae, scattering heavier elements into space. These explosions enriched the surrounding gas, planting the seeds for the next generations of stars, planets, and eventually, life. As the first galaxies lit up, their combined radiation began a grand transformation called reionization. This process cleared the cosmic fog, turning opaque space into a transparent expanse. Light could finally travel freely, stretching across the universe, reaching areas that had been hidden in darkness for hundreds of millions of years. Reionization didn't happen all at once. It was patchy, gradual, like the first hints of dawn breaking over a dark landscape. Some regions cleared early, glowing with ultraviolet light, while others remained shrouded in neutral hydrogen for longer. Over time, these luminous bubbles merged, and the universe became a vast, interconnected network of light and structure. Observing cosmic dawn is like peering through a window into the universe's youth. The light from these first galaxies has traveled over 13 billion years to reach us. Because of the universe's expansion, that light is stretched, shifted toward the red end of the spectrum, and faint but detectable with modern telescopes. Each photon carries information about the conditions of the early universe, the temperature of gas, the rate of star formation, the presence of heavy elements, and the structure of early galaxies. It's a delicate message from a time long before Earth, the Sun, or even our galaxy existed. During this epoch, stars formed in rapid bursts, some lasting only a few million years. Their energy heated surrounding gas, regulating further star formation. Gravity continued to pull matter together, merging small galaxies into larger systems, gradually building the first cosmic structures that would evolve into the grand galaxies we know today. These mergers were slow and majestic, taking millions of years, but each contributed to the intricate tapestry of the cosmos. Over time, these early galaxies laid the foundation for galaxy clusters and the large-scale structure of the universe. Some of the first stars were truly massive, much bigger than our sun, and they burned with incredible intensity. When they died as supernovae, they produced gamma-ray bursts, brief but brilliant flashes of energy that lit up the universe. These explosions enriched the interstellar medium with elements like carbon, oxygen, and iron, the building blocks of planets and life. Without these first generations of stars, the universe would have remained a simple primordial mix of hydrogen and helium. Their light, their explosions, and their remnants shaped everything that came after, including the atoms in our own bodies. The formation of these first galaxies also set the stage for cosmic magnetic fields. As gas collapsed and stars formed, tiny magnetic fields amplified, influencing the motion of charged particles, guiding star formation, and shaping the dynamics of early galaxies. These fields were weak at first, but became integral to galactic evolution, threading through the interstellar medium and helping to regulate the cosmic dance of matter. Even today, galaxies are still shaped by these magnetic forces, invisible but essential, connecting the earliest stars to the grand cosmic structures we observe. During cosmic dawn, black holes were also forming at the centers of these early galaxies. As matter fell into these newborn black holes, they began to launch jets, releasing energy that influenced the surrounding gas. These early jets may have helped regulate star formation and shaped the first galaxies, just as supermassive black holes influence modern galaxies. The interplay between gravity, radiation, and magnetic fields during cosmic dawn was delicate and complex, but it created the foundation for the universe we see today. Cosmic dawn was also a time of rapid change in the chemical composition of the universe. Early stars forged heavier elements in their cores, and their explosions spread these metals into space. These elements cooled gas clouds more efficiently, allowing the next generations of stars to form in different ways. Planetary systems began to become possible, and the universe became increasingly complex. Looking back at cosmic dawn, it's amazing to consider how small and fragile those first galaxies were compared to the sprawling spirals we see today. Yet, in their brief flickers of light, they shaped the entire cosmic landscape. Each one contributed to the clearing of the cosmic fog, each explosion scattered the ingredients for planets, and each gravitational pull helped organize matter into the first large-scale structures. The universe was young, chaotic, and beautiful, a quiet workshop where the first sparks of light brought order to darkness. The study of cosmic dawn continues to surprise us. New telescopes like the James Webb Space Telescope are peering deeper into space than ever before, revealing galaxies that formed even earlier than previously thought. Each discovery challenges our understanding, showing that the universe was forming structures faster and in more complex ways than models predicted. Observing these ancient galaxies is like reading the earliest pages of a cosmic diary, where every star, every burst of light tells a story of creation, transformation, and growth. As we drift through the universe in our imagination tonight, picture these first galaxies as tiny candles in an endless dark room, flickering to life, one by one. Their light stretches across billions of years to reach us, a gentle reminder that the cosmos was alive long before we existed, quietly building the structures that would one day host our sun, our planet, and ourselves. Cosmic dawn is a story of patience, persistence, and transformation, a testament to the slow, majestic unfolding of the universe from darkness into light. Every photon from these first galaxies is a message, a whisper from the past. They carry information about star formation, galaxy growth, chemical enrichment, and the clearing of the cosmic fog. By capturing these photons, astronomers reconstruct the history of cosmic dawn, revealing the intricate processes that shaped the universe's early evolution. Even though it happened billions of years ago, the echoes of cosmic dawn are still with us, a subtle glow that connects the present universe to its earliest days. Cosmic dawn reminds us that the universe is always evolving. Even in darkness, there is potential waiting for the right conditions to ignite. The first galaxies were proof that light could emerge from nothing, that order could arise from chaos, and that the cosmos is a place of constant change and wonder. As you imagine these ancient galaxies tonight, remember that the universe's story began with them, and in their light, we see the first chapter of everything we know. After cosmic dawn, when the first galaxies flickered to life, the universe still wasn't fully open to light. Space was filled with neutral hydrogen gas, and for millions of years this gas absorbed most of the ultraviolet light streaming from those early stars. The universe was partially opaque, a hazy expanse where light struggled to travel far. But the universe had more surprises in store. The first stars, galaxies, and early quasars pumped out radiation with enough energy to ionize hydrogen, kicking electrons off their atoms. This process, called reionization, was like slowly lifting a fog over a vast cosmic landscape, allowing light to finally travel freely across space. It was patchy and uneven, a slow transformation that lasted hundreds of millions of years. Some regions, dense with galaxies, cleared first, glowing with ultraviolet light, while vast empty patches remained shrouded in hydrogen fog. Over time, these clear regions expanded, merging into larger transparent zones, until eventually most of the universe became open to light. This transition fundamentally changed the appearance of the cosmos, revealing a universe full of structure, color, and depth. During this epoch, radiation from early stars and galaxies carved channels through the neutral hydrogen. Each ionizing photon created tiny bubbles of transparent gas, and as more stars formed, these bubbles grew, overlapping and connecting. Imagine countless tiny lanterns lighting up a dark forest, one by one, until the entire landscape was illuminated. That's essentially what reionization looked like on a cosmic scale, though stretched over millions of years. Quasars, the supermassive black holes at the centers of early galaxies, also played a key role. As matter spiraled into these black holes, enormous amounts of energy were released in the form of ultraviolet and X-ray light. These jets of radiation pierced the hydrogen fog, ionizing gas across vast distances. Even though quasars were rare compared to galaxies, their intense luminosity made them important contributors to the clearing of the cosmic haze. Reionization had lasting effects on galaxy formation. The ionized gas was hotter and more energetic than neutral hydrogen, which affected how gas collapsed to form new stars. In some regions, it slowed down star formation by preventing gas from cooling efficiently, while in other regions the radiation may have triggered bursts of star formation by compressing gas clouds. It was a delicate interplay, a cosmic push and pull, where radiation and gravity danced together to shape the universe's structure. Observing reionization today is like peeking through a keyhole into the universe's teenage years. Astronomers rely on distant quasars, galaxies, and the faint glow of neutral hydrogen itself to reconstruct this transformation. The light from these objects has traveled billions of years to reach us, carrying information about the timing, pace, and unevenness of reionization. By studying how much light was absorbed by hydrogen along the way, scientists can map which regions became transparent first and which lagged behind, piecing together a 3D view of the early cosmos. Reionization also connects to the cosmic microwave background. Even though the CMB was released long before this epoch, its photons interact with free electrons produced during reionization, slightly altering their polarization. These subtle effects are measurable and provide an indirect way to study when and how reionization occurred. It's a cosmic fingerprint, a delicate echo of the universe's second major phase change. the universe's transparency transformed how we observe everything afterward. Light could now travel freely across vast distances, carrying messages from galaxies forming billions of years away. This allowed the large-scale structure of the universe to be illuminated, revealing filaments, clusters, and voids. Cosmic transparency set the stage for all astronomical observations, making it possible to witness the universe's evolution in exquisite detail, from early galaxies to modern clusters. The chemical composition of the universe also began to diversify during reionization. Early supernovae had already seeded space with heavier elements, but ionized regions enabled new waves of star formation in gas enriched with these elements. Stars could form more efficiently, planets could start assembling from metals and dust, and the building blocks of life became more widespread. Reionization didn't just clear the fog, it set the conditions for complexity, making the universe richer and more interesting. In this period, cosmic light traveled longer distances than ever before. Photons escaping early galaxies were no longer trapped, allowing astronomers billions of years later to detect them. By analyzing this light, scientists determined the ages of galaxies, the rate of star formation, and the density of ionized versus neutral hydrogen. Each photon is a time traveler, whispering the secrets of a universe that was once opaque and mysterious. Reionization wasn't uniform. Dense regions with many galaxies ionized faster than emptier areas. This patchiness created a complex cosmic web of light and darkness. Some bubbles expanded and merged rapidly, while others lagged behind, creating pockets of neutral hydrogen. This unevenness tells us that even the early universe had variety and structure, a foreshadowing of the cosmic tapestry we see today with filaments, clusters, and voids. The effects of reionization are still detectable. Absorption lines in the spectra of distant quasars show the presence of remaining neutral hydrogen, revealing the tail end of reionization. These observations let astronomers date when most of the universe became transparent, showing that, by about 1 billion years after the Big Bang, reionization was largely complete. That's still more than 12 billion years ago, and yet its fingerprints remain in the light we observe today. Imagine standing in a dark forest, watching lanterns gradually light up every tree, branch, and clearing. That's cosmic reionization on an unimaginable scale, unfolding across hundreds of millions of light years and millions of years of time. It transformed the universe from a foggy, silent expanse into a bright, structured cosmos where light could finally journey freely and matter could assemble into the galaxies, stars, and planets we know today. Reionization is a reminder of the universe's patience. Even after hundreds of millions of years of darkness, small sparks, the first stars and galaxies slowly illuminated the cosmos. Light spreads, structures form, and transparency emerges. It's a slow, majestic process, a cosmic symphony that transformed chaos into clarity. By studying this epoch, astronomers gain perspective on the forces that shape the universe. Gravity pulls, radiation pushes, and together they orchestrate the formation of stars, galaxies, and clusters. Reionization is not just a chapter in cosmic history, it's the moment the universe learned to shine, the point where light claimed dominance over darkness. As we drift through this story tonight, imagine the first galaxy's light reaching out across space, slowly clearing the fog. Picture the ultraviolet radiation streaming through hydrogen, the faint glow of distant quasars piercing pockets of darkness, and the merging bubbles of transparency forming a new, luminous cosmos. This was a universe awakening, moving from quiet potential to vibrant structure, preparing for the richness and complexity that would follow. Reionization is also a gentle reminder of time's scale. Millions of years pass in what feels like an instant to the cosmos, yet for us, these epochs are almost unimaginable. The processes that cleared the universe, made it transparent, and enabled complex structures took patience, repetition, and cosmic rhythm. It's a story of gradual transformation, subtle but profound, showing how even the smallest sources of light can eventually illuminate the darkest corners of existence. By the end of reionization, the universe was ready for the next chapters: galaxy growth, star formation, planetary assembly, and eventually life. Transparency allowed light to travel, information to propagate, and structure to organize. The universe had passed its first major threshold, moving from a foggy, hidden place to a visible, observable, and richly patterned cosmos. Every star, every galaxy, every photon traveling through space today owes its clarity to this pivotal epoch. And as you listen tonight, imagine being a silent observer floating through this early universe. Watch the fog lift, watch galaxies ignite and radiation fill the emptiness, and feel the universe stretching out, becoming clear, expansive, and alive. This is reionization, a slow, beautiful unveiling of the cosmos, a transformation that set the stage for everything that followed, including us, and a story that still echoes through the light traveling toward our eyes from billions of years ago. After the universe became transparent, it still had secrets lurking in its depths. Among the most mysterious were the first supermassive black holes, monsters with millions or even billions of times the mass of our Sun. These giants formed surprisingly fast. In just a few 100 million years after the Big Bang, scientists are still piecing together exactly how they grew so quickly. But one thing is clear: they had a profound effect on the universe around them. Supermassive black holes aren't just hungry cosmic vacuum cleaners. When they pull in gas and dust, they create enormous disks of hot material swirling at near-light speeds. This disk glows brilliantly, shining across the universe with light and radiation that can outshine entire galaxies. These early black holes acted like cosmic lighthouses, their energy shaping the evolution of nearby gas and stars. Wherever a black hole fed, it influenced star formation, sometimes slowing it down by heating gas, sometimes triggering bursts of creation by compressing clouds. Some of these black holes launched colossal jets of particles that traveled millions of light-years into intergalactic space. Imagine streams of charged particles blasting out from both poles at nearly the speed of light, carving tunnels through the surrounding gas. These jets sculpted their host galaxies, reshaping their environments and regulating the growth of stars. They acted as cosmic artists, drawing patterns in matter on scales we can barely comprehend. Observing these jets is like watching a cosmic fireworks show in slow motion. The jets are incredibly energetic, carrying more power than all the stars in a galaxy combined. They twist and bend as they interact with magnetic fields and interstellar gas, creating stunning arcs and filaments of glowing material. Even though they may be millions of light-years away, we can detect their presence because of the radiation they emit, from radio waves to X-rays. The first supermassive black holes were also connected to the formation of early galaxies. As galaxies merged and grew, their central black holes merged as well, becoming even more massive. Each merger sent ripples through space-time, releasing gravitational waves that we can now detect with sensitive instruments on Earth. These cosmic collisions were rare, but when they happened, they reshaped the surrounding environment, triggering bursts of star formation and stirring gas across thousands of light-years. Despite their massive size, these black holes are invisible in the traditional sense. We don't see the black holes themselves, only their influence. We see stars orbiting around an invisible center, jets of particles blasting through space, and disks of hot material glowing brightly. This invisibility adds to their mystery, making them some of the most fascinating objects in the universe. Jets from supermassive black holes aren't constant. They flare and fade, influenced by the black hole's feeding habits. When a black hole consumes a lot of gas quickly, the jets grow stronger and brighter. When the fuel supply runs low, the jets weaken, sometimes disappearing altogether for long periods. This variability means that black holes are dynamic, living objects in a way, interacting with their environment across millions of years. These early black holes also shaped the distribution of matter in the universe. Their radiation and jets pushed gas away from galactic centers, preventing runaway star formation and keeping galaxies from collapsing entirely under their own gravity. By regulating the growth of stars and gas, supermassive black holes played a subtle but crucial role in the cosmic balance. Without them, galaxies might have evolved in very different ways. The formation of the first black holes is still a puzzle. Some may have formed from the direct collapse of massive gas clouds, bypassing the ordinary star phase. Others may have grown from the remnants of the first generation of massive stars, merging and feeding over time. Whatever the path, the result was the same: enormous objects with gravitational pull so strong that not even light can escape, shaping the universe around them in ways both dramatic and gentle. Jets from these black holes also influence the intergalactic medium, the gas between galaxies. By injecting energy and stirring the gas, they helped mix elements and heat the surrounding material, preparing it for future star formation. These jets essentially connected galaxies to the broader cosmic environment, showing that nothing in the universe exists in isolation. Every galaxy, every cloud of gas, every bit of dust is part of a vast interconnected web influenced by these cosmic giants. Observing the first supermassive black holes gives us a window into the universe's youth. Their light has traveled billions of years to reach us, telling stories of rapid growth, cosmic fireworks, and environmental influence. Each observation is like a time machine, letting us see these objects as they were in the early universe, when galaxies were still forming and the cosmos was younger, more raw, and full of surprises. Supermassive black holes also teach us about energy on scales we can hardly imagine. The jets carry particles at nearly the speed of light, generating shock waves and magnetic turbulence across millions of light years. This energy shapes the universe, moving matter around, triggering star formation, and sometimes clearing gas from entire galaxies. It's a cosmic dance of creation and destruction, a reminder that even in the darkest places, energy flows and transformation occurs. Even though these black holes are millions or billions of times more massive than our Sun, they are tiny compared to the space around them. The gravitational influence is vast, but the physical size is small relative to the galaxy. This contrast tiny objects with enormous effects makes them fascinating. They are a reminder that in the universe, size doesn't always determine importance, influence does. The first supermassive black holes also connect to other cosmic phenomena. They are linked to high-energy cosmic rays, to gravitational waves, and to the growth of galaxies. They are responsible for some of the brightest quasars observed, lighting up the universe at a time when most of space was still dark. Their presence explains many of the patterns we see today, from galaxy shapes to intergalactic gas distribution. Jets from black holes are also a guide to extreme physics. Conditions near a black hole cannot be replicated on Earth. Magnetic fields, velocities, and densities are beyond our imagination. By studying these jets, scientists can test theories of relativity, magnetism, and particle acceleration, using the universe as a laboratory. Every photon from these jets carries information about physics under extreme conditions, a natural classroom for understanding the laws of nature. Even today, as we observe supermassive black holes in distant galaxies, their effects are ongoing. They continue to regulate star formation, shape gas flows, and emit energy across the electromagnetic spectrum. They are both destructive and creative, clearing paths while enabling new stars to form. Their influence is subtle, yet pervasive, a reminder of the dynamic processes that govern the universe. Thinking about these giants can be calming in a strange way. They are constant, massive, and enduring, silently shaping the universe over billions of years. While we go about our daily lives, these black holes continue their cosmic work, a quiet reminder of the vastness and continuity of the cosmos. They show that even the most invisible forces can leave lasting marks on the universe. And as you imagine these supermassive black holes tonight, picture jets streaming out across millions of light years, shaping galaxies, stirring gas, and lighting up the dark universe. Imagine the first quasars blazing brightly, signaling the arrival of massive energy and structure into a still young cosmos. Think of gravity, radiation, and magnetic fields all working together to sculpt the universe. And know that while it all feels distant, we are connected, witnessing these stories across space and time, letting them whisper into our imagination as we drift closer to sleep. As your mind drifts deeper into the quiet, you've traveled from the fiery birth of the universe to the gentle glow of distant stars. You've seen the first galaxies ignite, watched black holes sculpt entire galaxies with their jets, and felt the invisible threads of dark matter guide cosmic flows across unimaginable distances. Every atom around you, every bit of stardust, has a story stretching back billions of years, and tonight you're part of that story too. Imagine floating above the spiral arms of the Milky Way, seeing countless stars twinkle, each one a sun with its own planets, perhaps its own secrets. Imagine gliding past cosmic filaments, long, slender highways of dark matter and gas connecting galaxies like veins in a grand cosmic body. Feel the calm of space, where nothing rushes, yet everything moves, perfectly in rhythm over eons. The universe doesn't hurry, it doesn't stress, it just unfolds. And you, tucked in your warm bed, are allowed to drift alongside it, quietly watching the cosmic dance. Picture the cosmic microwave background, the oldest light we can see. It wraps the universe in a faint, soft glow, a relic from the time when the universe was just 380,000 years old. It's a whisper from the past, a reminder that everything has a beginning, everything evolves, and everything is connected. Even the atoms in your body were once part of distant stars, forged in fiery furnaces and scattered across space. That means, in a very real way, the universe flows through you. You are stardust, you are cosmic history, you are part of this grand unfolding story. As your thoughts float through these ancient galaxies, notice the gentle hum of cosmic events around you. Supernova explosions light up the void for brief moments, gamma-ray bursts flare across billions of light-years, and jets from black holes carve glowing paths through interstellar gas. These events are massive, powerful, and awe-inspiring, yet they happen with patience, on scales far beyond human time. There's a rhythm here, a kind of cosmic breathing, and it's comforting. It's a reminder that the universe, in all its vastness, has a balance. Even chaos has order, even violence has beauty. Think about the cosmic voids, enormous stretches of almost empty space, quietly guiding the motion of galaxies along invisible currents. And then, picture the filaments crisscrossing these voids like delicate threads, carrying matter and energy, linking galaxies, clusters, and superclusters. The contrast is poetic emptiness, shaping presence, darkness, giving structure. quiet, defining motion. And you're witnessing it all in your mind, peacefully, without hurry, without worry, letting each detail sink into your imagination. Cosmic time stretches far beyond anything we can feel in our daily lives. 1 second for a photon traveling from a distant quasar may span millions of years in human terms. And yet, even in this immense scale, there is beauty. Each galaxy, each star, each particle contributes to the overall pattern. Nothing is wasted, nothing is random. Even cosmic rays raining down on Earth subtly shape life and evolution. The universe whispers its secrets to those willing to listen, and tonight your mind is listening, softly, with curiosity and awe. Imagine the gentle pull of gravity guiding stars and galaxies, the magnetic fields threading through spirals, the relic neutrinos streaming through every corner of space. Every tiny particle, every faint photon, every whisper of radiation contributes to a story billions of years in the making. It's a story without rush, without interruption, a story that invites you to relax, to breathe, to feel at peace with the enormity of existence. Now picture the first moments of cosmic dawn again, when the universe transitioned from darkness to light. Primordial clouds collapsed under gravity, stars ignited, galaxies formed, and reionization cleared the fog from the cosmos. This was the universe's first illumination, a soft awakening. And tonight, in your own way, you are experiencing a similar moment, allowing your mind to awaken to the majesty of everything around you while sinking into calm. Let the glow of that first light mingle with the comfort of your bed, with the gentle rhythm of your breath, carrying you deeper into rest. The stories of cosmic evolution continue endlessly. Stars are born and die. Black holes consume and sculpt, galaxies merge and flow along invisible currents. You can let your imagination wander among these processes, knowing they happen on scales both enormous and patient, unfolding over billions of years. There's no need to rush. There's no need to grasp everything. Just float, observe, and let the universe wash over you, gently and slowly, like a soft tide. As you drift, remember that this vast universe is intimately connected to you. The same physics shaping distant galaxies shapes your body, your planet, your very thoughts. The oxygen you breathe, the calcium in your bones, the carbon in every cell, all originated in stars long gone. You are a product of cosmic history. You are a living thread in a tapestry woven over 13.8 billion years. That connection can be grounding, soothing, and deeply comforting. You are part of something much bigger, something enduring and beautiful. And now, as your thoughts soften and your eyelids grow heavier, imagine the universe continuing its quiet dance. Light streams across billions of light years. Cosmic rays ripple through space, black holes hum their silent songs, and galaxies drift along their invisible filaments. You are here, a small but integral part of this magnificent story, floating gently in the warmth of your own existence. Let this sense of connection lull you further into rest, into dreams, into the peaceful surrender of sleep. Before you fully drift away, remember this: the universe, in all its vastness, continues its quiet, rhythmic unfolding. And if tonight's journey through cosmic wonders brought even a spark of calm, curiosity, or awe, you're invited to stay with us on this journey. Subscribe to Sleepy Science and let us guide you through more galaxies, more stardust, more cosmic secrets. Each video is a soft doorway into the cosmos, a gentle exploration to calm your mind, ignite your imagination, and carry you into restful sleep. You don't just watch, you become part of the story, part of the universe's quiet song. So close your eyes, take a deep breath, and let the universe cradle you. Sleep well, dream softly, and remember, the stars are always there, quietly shining, patiently waiting, inviting you to return for another journey. Good night.